What if everything you see is just a fragment, a thin slice of something infinitely more complex? Our universe might be nothing more than a projection, controlled by dimensions we cannot see or comprehend. Theoretical physicists have long suspected that our three-dimensional world is merely a window into a much larger, more intricate cosmic structure. The concept of hidden dimensions isn't just science fiction. It's a serious scientific hypothesis that could explain some of the universe's most profound mysteries. String theory suggests we live in a multiverse with up to 11 dimensions. Most of them folded so small we can't perceive them. Imagine our reality as a vast web, with most of its threads invisible to the naked eye. These hidden dimensions could be controlling fundamental forces, bending the very fabric of space and time. In physics, a dimension is a fundamental aspect of space or time that we use to describe and measure the universe around us. The most familiar dimensions are the three spatial dimensions of length, width, and height, which allow us to pinpoint the location of any object in our everyday world. These dimensions give us the ability to move forward and backward, left and right, and up and down. Time is often considered the fourth dimension, as it allows us to describe when events occur and how they unfold. Together, these four dimensions form what physicists call spacetime, a concept that combines space and time into a single continuum. However, the concept of dimensions extends beyond these familiar four. Some theories in physics, such as string theory, propose the existence of additional dimensions beyond what we can directly observe. These extra dimensions might be extremely small, curled up in ways that make them imperceptible to our current methods of measurement. Dimensions play a crucial role in our understanding of the universe, from the behavior of subatomic particles to the large-scale structure of the cosmos. They provide the framework within which we formulate physical laws and theories, helping us to describe and predict the behavior of everything from the smallest quantum particles to the largest galaxies. In our everyday experience, we are primarily aware of four dimensions. Three of these are spatial dimensions: length, width, and height. These allow us to navigate and understand the physical world around us, giving objects their shape and allowing us to move in different directions. The fourth dimension we regularly perceive is time. Although we cannot see or touch time directly, we experience its passage and use it to measure the duration of events and the sequence in which they occur. Time allows us to distinguish between past, present, and future, and plays a crucial role in how we understand cause and effect. These four dimensions form the foundation of what physicists call spacetime, a concept that combines the three spatial dimensions with time into a single continuum. This framework is essential for understanding many aspects of our universe, from the motion of objects to the behavior of light. While these four dimensions dominate our everyday perception, theoretical physics suggests the possibility of additional dimensions beyond those we can directly observe. These extra dimensions, if they exist, could help explain some of the mysteries of the universe that current theories struggle to address. Spacetime consists of four dimensions that describe our universe. Three of these dimensions are spatial, representing the familiar concepts of length, width, and height. These spatial dimensions allow us to pinpoint the location of any object in three-dimensional space. The fourth dimension, however, is time itself. This temporal dimension is crucial for understanding the fabric of our universe. It allows us to describe when events occur and how they relate to one another chronologically. By combining space and time into a single concept, physicists can better explain the behavior of objects and the propagation of light through the cosmos. In everyday life, we often think of space and time as separate entities. However, Einstein's theory of relativity revealed that they are intimately connected. The speed of light remains constant for all observers, regardless of their motion. This fundamental fact leads to the realization that space and time must be flexible, stretching or contracting depending on an observer's frame of reference. Understanding spacetime as a four-dimensional continuum has profound implications for our view of the universe. It helps explain phenomena such as time dilation and length contraction, where time passes more slowly and distances appear shorter for objects moving at high speeds. This four-dimensional framework also forms the foundation for our modern understanding of gravity, describing it as the curvature of spacetime caused by massive objects. Scientists define higher dimensions as additional spatial or temporal directions beyond the familiar three dimensions of space and one dimension of time we experience in our everyday lives. These extra dimensions are mathematical constructs that help explain complex phenomena in physics and cosmology. In string theory, for instance, scientists propose the existence of 10 or 11 dimensions to reconcile quantum mechanics with gravity. These additional dimensions are thought to be tightly curled up and imperceptible at human scales, yet they play a crucial role in the fundamental workings of the universe. Higher dimensions can be conceptualized as directions of movement or measurement that are perpendicular to all other known dimensions. For example, a four-dimensional cube called a tesseract would extend in a direction perpendicular to length, width, and height. While difficult to visualize, these extra dimensions provide a framework for understanding concepts like parallel universes and the nature of subatomic particles. The study of higher dimensions allows scientists to develop more comprehensive models of reality, potentially unlocking secrets about the origins of the universe, dark matter, and the unification of fundamental forces. As our understanding grows, these abstract concepts may lead to groundbreaking discoveries in physics and cosmology. Dimensions are crucial to our understanding of the universe because they form the fundamental framework in which all physical phenomena occur. In our everyday experience, we perceive three spatial dimensions: length, width, and height, along with time as a fourth dimension. This four-dimensional structure, known as spacetime, allows us to describe the position and movement of objects and events. However, the concept of dimensions extends far beyond our immediate perceptions. Some theories in physics, such as string theory, propose the existence of additional spatial dimensions beyond the familiar three. These extra dimensions could potentially explain fundamental forces and particles in ways that our current models cannot. Understanding dimensions also helps us grasp the scale and structure of the universe. From the subatomic realm to the vastness of cosmic voids, different phenomena operate at various dimensional scales. For instance, quantum mechanics deals with extremely small scales, while general relativity describes the behavior of space, time, and gravity on cosmic scales. Moreover, dimensions play a crucial role in cosmological models. The shape and curvature of space itself can be described using dimensional concepts, influencing our understanding of the universe's overall geometry and its potential fate. By exploring the nature of dimensions, scientists continue to unravel the deepest mysteries of our cosmos, from its origin to its ultimate destiny. Spatial and temporal dimensions are fundamental aspects of our universe, each playing a distinct role in how we perceive and interact with reality. Spatial dimensions refer to the three directions in which we can move and measure distances: up and down, left and right, forward and backward. These dimensions allow us to describe the position and size of objects in space. We can walk around a building, measure its height, or calculate the distance between two cities using spatial dimensions. Temporal dimension, on the other hand, relates to time. Unlike spatial dimensions, we can only move in one direction through time, forward. We experience time as a continuous flow of events from past to present to future. The temporal dimension allows us to sequence events, measure durations, and understand cause and effect relationships. While we can freely navigate through spatial dimensions, our experience of the temporal dimension is more constrained. We can choose to move left or right, up or down, but we cannot choose to move backward in time or jump ahead to the future. This asymmetry between spatial and temporal dimensions is a fundamental feature of our universe and plays a crucial role in shaping the laws of physics. The interplay between spatial and temporal dimensions gives rise to the concept of spacetime, a four-dimensional framework that combines the three spatial dimensions with time. This unified view of space and time, proposed by Albert Einstein in his theory of relativity, revolutionized our understanding of the universe and continues to be a cornerstone of modern physics. Our understanding of dimensions has undergone a remarkable transformation throughout history. Ancient civilizations primarily viewed the world in terms of three spatial dimensions: length, width, and height. This basic concept allowed for practical applications in architecture, navigation, and everyday life. The scientific revolution of the 16th and 17th centuries brought about a more rigorous mathematical approach to dimensions. René Descartes introduced the Cartesian coordinate system, which provided a way to describe points in space using numbers. This innovation laid the groundwork for more advanced geometric concepts and paved the way for future developments in physics and mathematics. A significant leap came in the late 19th and early 20th centuries with the introduction of spacetime. Albert Einstein's theory of special relativity proposed that time should be considered as a fourth dimension, intricately linked with the three spatial dimensions. This revolutionary idea fundamentally changed our perception of the universe and led to profound implications in physics and cosmology. In recent decades, theoretical physicists have explored the possibility of additional dimensions beyond the four we can directly observe. String theory, for instance, proposes that our universe might contain as many as 10 or 11 dimensions, most of which are curled up and imperceptible in our everyday experience. These extra dimensions could potentially explain fundamental forces and particles in ways that our current four-dimensional models cannot. Dimensions play a crucial role in modern physics theories, shaping our understanding of the universe and its fundamental workings. In classical physics, we typically deal with three spatial dimensions and one time dimension, forming the familiar four-dimensional spacetime of our everyday experience. However, advanced theories in physics propose the existence of additional dimensions beyond these four. String theory, a prominent candidate for a unified theory of physics, suggests that our universe might contain as many as 10 or 11 dimensions. These extra dimensions are thought to be tightly curled up and incredibly small, existing at scales far beyond our current ability to detect directly. These hidden dimensions could potentially explain some of the mysteries that continue to puzzle physicists, such as the nature of dark matter and dark energy. The concept of higher dimensions also plays a significant role in theories attempting to reconcile quantum mechanics with general relativity. These extra dimensions provide a framework for explaining gravity's apparent weakness compared to other fundamental forces, as gravity might be leaking into these additional dimensions. Furthermore, the idea of multiple dimensions has led to intriguing concepts like parallel universes and the multiverse theory. These theories propose that our universe might be just one of many, existing alongside countless others in a vast multi-dimensional cosmos. While still speculative, these ideas continue to drive research and expand our understanding of the nature of reality itself. When we talk about higher dimensions, we're venturing beyond the familiar three-dimensional world we experience every day. Our universe has three spatial dimensions: length, width, and height, plus time as a fourth dimension. But theoretical physics suggests the possibility of additional dimensions beyond these four. These higher dimensions aren't something we can directly see or touch. They're mathematical concepts that help explain certain phenomena in physics. For instance, string theory, a framework attempting to unify fundamental forces, proposes that our universe might have 10 or even 11 dimensions. In these extra dimensions, reality could behave in ways that seem impossible in our three-dimensional space. Objects might be able to move in directions we can't perceive or exist in multiple places simultaneously. These higher dimensions could potentially explain mysteries like dark matter, dark energy, or even the nature of gravity. While we can't observe these dimensions directly, scientists are developing experiments to detect their effects indirectly. The concept of higher dimensions challenges our perception of reality and pushes the boundaries of our understanding of the universe. The concept of higher dimensions challenges our perception of reality and pushes the boundaries of our understanding of the universe. The number of dimensions theoretically possible extends far beyond our everyday experience of three spatial dimensions and one dimension of time. String theory, a prominent framework in theoretical physics, suggests that our universe might actually contain 10 or 11 dimensions. This concept challenges our conventional understanding of reality and opens up fascinating possibilities for the structure of the cosmos. While we can easily visualize three spatial dimensions, length, width, and height, and conceptualize time as a fourth dimension, the additional dimensions proposed by string theory are much harder to grasp. These extra dimensions are thought to be compactified, meaning they are curled up so tightly that they are imperceptible in our macroscopic world. Their existence could potentially explain fundamental aspects of particle physics and gravity that currently elude our understanding. Interestingly, some theories push the boundaries even further. Certain versions of string theory and its extension, M theory, propose the existence of a multiverse with potentially infinite dimensions. In this scenario, our universe might be just one of many, each with its own set of physical laws and dimensional configurations. It is important to note that these higher dimensional models remain theoretical. While they offer elegant mathematical solutions to some of the most perplexing questions in physics, direct experimental evidence for dimensions beyond the familiar four of spacetime remains elusive. The search for proof of these extra dimensions continues to drive cutting-edge research in particle physics and cosmology. String theory proposes that the fundamental constituents of the universe are not point-like particles, but tiny, vibrating strings of energy. These strings are thought to be incredibly small, much smaller than an atom or even a proton. According to this theory, the different vibrations of these strings give rise to all the particles and forces we observe in nature. One of the most intriguing aspects of string theory is its requirement for additional spatial dimensions beyond the three we experience in our everyday lives. While we perceive a universe with three spatial dimensions and one dimension of time, string theory suggests that there might be as many as 10 or 11 dimensions in total. These extra dimensions are thought to be tightly curled up and incredibly small, explaining why we do not directly observe them. The existence of these higher dimensions is crucial for string theory to work mathematically. They provide the necessary space for strings to vibrate in complex ways, allowing for the diverse array of particles and forces we see in our universe. Without these extra dimensions, the equations of string theory would not be consistent or yield meaningful results. The concept of higher dimensions in string theory also offers potential explanations for some of the mysteries in physics. For instance, it might help reconcile the apparent weakness of gravity compared to other fundamental forces, or provide insights into the nature of dark matter and dark energy. While string theory remains unproven and highly controversial, its exploration of higher dimensions continues to inspire new ways of thinking about the fabric of our universe. M-theory is an ambitious framework in theoretical physics that attempts to unify various versions of string theory. It suggests that our universe consists of 11 dimensions, far beyond the 3 spatial dimensions and 1 time dimension we experience in our daily lives. These additional dimensions, according to M-theory, are typically hidden from our perception, existing at scales so small that they are beyond our current ability to detect or measure directly. The theory proposes that these extra dimensions are tightly curled up or compactified, making them invisible to us, but crucial for explaining fundamental aspects of the universe. M-theory builds upon the groundwork laid by string theory, which initially proposed that all matter and energy in the universe are composed of tiny, vibrating strings. By incorporating these 11 dimensions, M-theory aims to reconcile the seemingly incompatible theories of general relativity and quantum mechanics, potentially offering a unified description of all fundamental forces and particles in nature. While M-theory remains highly speculative and lacks experimental evidence, it continues to intrigue physicists with its potential to provide a comprehensive understanding of the universe's most fundamental workings. The concept of multiple dimensions challenges our intuition and pushes the boundaries of our understanding of reality. Mathematicians approach higher dimensions by extending the principles we observe in our familiar 3-dimensional world. They use analytical tools and abstract reasoning to explore spaces beyond what we can physically perceive or visualize. One key concept is the idea of coordinates. Just as we use 3 numbers to specify a point in 3-dimensional space, mathematicians use 4, 5, or even more numbers to define locations in higher dimensional spaces. Each additional coordinate represents a new direction that is perpendicular to all the others. Mathematicians also employ analogies and geometric intuition. They might consider how a 2-dimensional being would perceive a 3-dimensional object passing through their flat world, then extrapolate this to how we might interpret glimpses of 4-dimensional objects in our 3-dimensional reality. This approach helps in developing intuition about higher dimensional phenomena. Advanced mathematical techniques such as linear algebra and tensor calculus provide powerful tools for manipulating and analyzing higher dimensional spaces. These methods allow mathematicians to study the properties of these abstract realms, uncovering patterns and relationships that often have surprising applications in physics, computer science, and other fields. A hypercube is a fascinating geometric concept that extends our understanding of cubes into higher dimensions. While we are familiar with cubes in our 3-dimensional world, a hypercube exists in 4 dimensions or more. Imagine starting with a single point which has 0 dimensions. By stretching that point, we create a line which has 1 dimension. Stretching that line perpendicular to itself gives us a square with 2 dimensions. Extending the square upwards produces a cube with 3 dimensions. Following this pattern, a hypercube is what we get when we extend a cube into a 4th spatial dimension. Though we cannot physically see or touch a 4-dimensional object, mathematicians and physicists use hypercubes to explore and explain higher dimensional spaces. Each step up in dimension adds more complexity to the shape. A 4-dimensional hypercube, also known as a tesseract, would have 16 vertices, 32 edges, and 24 faces, all existing in 4-dimensional space. Hypercubes relate to higher dimensions by providing a conceptual framework for understanding spaces beyond our everyday experience. They help scientists and mathematicians visualize and work with complex systems that require more than 3 dimensions to describe fully. For example, in physics, some theories propose that our universe might have additional spatial dimensions beyond the 3 we observe, and hypercubes offer a way to model and explore these ideas. The concept of hypercubes and higher dimensions has applications in various fields, from computer graphics and data visualization to quantum mechanics and string theory. By stretching our minds to comprehend these abstract shapes, we open doors to new ways of thinking about space, time, and the fundamental nature of our universe. The human brain, evolved to navigate a three-dimensional world, struggles to truly visualize higher dimensions. However, we can use mathematical concepts and analogies to grasp some aspects of higher dimensional spaces. One approach is to consider how a two-dimensional being might perceive three dimensions. Imagine a flat creature living on the surface of a sheet of paper. If a three-dimensional object passed through its world, the creature would only see cross-sections of that object as it intersected the paper. Similarly, we can think of four-dimensional objects passing through our three-dimensional space, appearing as changing three-dimensional shapes. Mathematicians and physicists use tools like projections and slices to represent higher dimensional objects in lower dimensions. For instance, we can create three-dimensional shadows of four-dimensional objects, much like how we see two-dimensional shadows of three-dimensional objects. These techniques allow us to study and work with higher dimensions, even if we cannot directly visualize them. While we cannot fully picture higher dimensions, understanding their properties helps us develop theories in physics and mathematics. Concepts like string theory and the multiverse rely on the existence of extra dimensions, pushing our understanding of reality beyond what we can see with our eyes alone. To grasp the concept of higher dimensions, scientists and mathematicians often employ various tools and analogies. One common approach is to start with lower dimensions and gradually build up. We begin with a zero-dimensional point, then move to a one-dimensional line, a two-dimensional plane, and a three-dimensional cube. This progression helps us visualize the pattern and imagine how it might continue into the fourth dimension and beyond. Another useful analogy is the concept of shadows. Just as a three-dimensional object casts a two-dimensional shadow, we can imagine our three-dimensional world as a shadow of a four-dimensional object. This idea, known as dimensional analogy, allows us to conceptualize how higher dimensional objects might interact with our familiar three-dimensional space. Computer simulations and mathematical models also play a crucial role in exploring higher dimensions. These tools allow scientists to manipulate and visualize complex geometric shapes that exist in four or more dimensions. By projecting these objects into three-dimensional space or creating cross-sections, researchers can study their properties and behavior. Everyday objects can serve as surprisingly effective analogies for higher dimensions. A book, for instance, can represent time as the fourth dimension. Each page represents a moment in time, with the entire book embodying the full timeline. This analogy helps illustrate how time might appear as a spatial dimension from a higher dimensional perspective, allowing us to better understand concepts like space-time in modern physics. Scientific theories and observations provide tantalizing hints about the existence of higher dimensions beyond the three spatial dimensions and one time dimension we experience in our daily lives. String theory, a leading candidate for a unified theory of physics, proposes that our universe actually contains 10 or 11 dimensions. These extra dimensions could be tightly curled up and incredibly small, explaining why we don't perceive them directly. The mathematical framework of string theory requires these additional dimensions to reconcile quantum mechanics with gravity. This elegantly solves many puzzles in particle physics and cosmology, offering a potential path to the elusive theory of everything. However, direct experimental evidence for these extra dimensions remains elusive. Some scientists have proposed that certain anomalies in gravitational measurements might be explained by the presence of extra dimensions. For instance, variations in the strength of gravity at very small scales could indicate that gravity is leaking into other dimensions. Experiments using powerful particle accelerators like the Large Hadron Collider also search for signs of extra dimensions, such as the creation of microscopic black holes or the detection of particles that could only exist if higher dimensions were real. Cosmological observations provide another avenue for investigating higher dimensions. The properties of cosmic inflation, dark energy, and the distribution of matter in the universe might be better explained by models incorporating extra dimensions. While none of these lines of evidence are conclusive, they continue to drive research and spark scientific curiosity about the true nature of our multidimensional reality. Particle accelerators are powerful tools that allow scientists to probe the fundamental nature of reality. By smashing particles together at incredibly high speeds, these machines create conditions similar to those present in the early moments of the universe. This enables researchers to study the behavior of matter and energy at the smallest scales, offering insights into the fabric of space and time itself. One of the key contributions of particle accelerators to our understanding of dimensions comes from their ability to explore higher energy states. As particles are accelerated to near light speed, they gain enormous amounts of energy. This energy can manifest as additional particles or reveal hidden properties of known particles. Some theories suggest that at extremely high energies, extra dimensions beyond the familiar three of space and one of time might become detectable. Some theories suggest that at extremely high energies, extra dimensions beyond the familiar three of space and one of time might become detectable. These experiments also help scientists test theories like string theory, which proposes that our universe might have many more dimensions than we can directly observe. While we experience only 4 dimensions in our everyday lives, particle accelerators allow researchers to search for evidence of these hidden dimensions through indirect means. For example, if extra dimensions exist, some of the energy from particle collisions might leak into these other dimensions, leading to unexpected results in the data collected. Furthermore, particle accelerators have helped confirm the existence of the Higgs boson, a particle that gives mass to other fundamental particles. This discovery has profound implications for our understanding of how matter interacts with the fabric of space-time, potentially shedding light on the nature of dimensions themselves. By continuing to push the boundaries of particle physics, accelerators may yet reveal more surprises about the dimensional structure of our universe. The discovery of the Higgs boson has profound implications for dimensional theories in physics. This elusive particle, first detected at the Large Hadron Collider in 2012, provides crucial support for the standard model of particle physics. However, its relatively low mass poses intriguing questions about the nature of our universe and the potential existence of extra dimensions. Some theories propose that the Higgs boson's observed mass can be explained by the presence of additional spatial dimensions beyond the 3 we experience. These extra dimensions could be tightly curled up, invisible to our everyday observations, but influencing the behavior of fundamental particles. In this context, the Higgs boson might be interacting with these hidden dimensions, affecting its properties and mass. Furthermore, the Higgs discovery has reinvigorated interest in supersymmetry, a theory that predicts a partner particle for every known particle in the standard model. Supersymmetry often goes hand in hand with string theory, which posits the existence of multiple dimensions. The search for supersymmetric particles continues, and their potential discovery could provide strong evidence for extra dimensions. The Higgs boson also plays a role in theories of quantum gravity, which attempt to reconcile general relativity with quantum mechanics. Some of these theories, like loop quantum gravity, explore the possibility that space itself is quantized at extremely small scales, potentially leading to additional dimensions or altered geometry at the quantum level. The properties of the Higgs boson could offer clues about the nature of space-time at these fundamental scales, guiding our understanding of dimensional theories and the structure of the universe. Gravitational waves, ripples in the fabric of space-time, offer a fascinating connection to the concept of higher dimensions. These waves, first predicted by Albert Einstein and later confirmed through observations, provide a unique way to explore the structure of our universe beyond the 3 spatial dimensions and 1 time dimension we typically experience. Some theories in physics, such as string theory, propose the existence of additional spatial dimensions beyond the familiar 3. These extra dimensions could be extremely small and curled up, invisible to our everyday observations. Gravitational waves might interact with these hidden dimensions in ways that could potentially be detected by our instruments. If higher dimensions exist, gravitational waves could behave differently than expected in a four-dimensional universe. They might propagate through these extra dimensions, leading to subtle variations in their strength or frequency as detected by our instruments on Earth. Scientists are actively searching for such anomalies in gravitational wave data, which could provide indirect evidence for the existence of higher dimensions. Moreover, certain models suggest that gravity itself might be stronger in higher dimensions, only appearing relatively weak in our observable universe. Gravitational waves could serve as a probe to test this idea, potentially revealing new insights into the fundamental nature of gravity and the structure of space-time itself. As we continue to improve our ability to detect and analyze gravitational waves, we may uncover clues about the hidden geometry of our universe and the potential reality of higher dimensions. Several astronomical observations provide tantalizing hints that support the concept of extra dimensions beyond the four we commonly experience. One intriguing piece of evidence comes from the study of gravity at cosmic scales. Scientists have noticed that gravity seems to behave differently at very large distances compared to what our current models predict. This discrepancy could potentially be explained by the existence of extra dimensions that allow gravity to leak into them, effectively weakening its force over vast cosmic distances. Another observation that lends support to the idea of extra dimensions is the accelerating expansion of the universe. The discovery that our universe is expanding at an increasing rate rather than slowing down as expected has led scientists to propose the existence of dark energy. Some theories suggest that this mysterious force could be the result of gravity's interaction with hidden dimensions, influencing the behavior of our visible universe. The study of cosmic inflation, the rapid expansion of the universe in its earliest moments, also provides some support for extra dimensions. Certain models of inflation incorporate additional spatial dimensions to explain the uniformity and flatness of the observable universe. These models can make predictions about the cosmic microwave background radiation that align closely with what we observe. While these observations do not conclusively prove the existence of extra dimensions, they offer intriguing possibilities that continue to drive research in theoretical physics and cosmology. As our observational techniques and technologies advance, scientists hope to uncover more evidence that could shed light on the true nature of our universe and the potential reality of dimensions beyond our everyday experience. Dark matter research and higher dimensional theories converge in fascinating ways, pushing the boundaries of our understanding of the universe. Scientists exploring dark matter have found that its behavior often defies explanation within the confines of our familiar three spatial dimensions and one time dimension. This has led some researchers to consider the possibility that dark matter might be influenced by or even originate from higher dimensions. String theory, a prominent framework in theoretical physics, proposes that our universe might contain up to 11 dimensions. In this context, dark matter particles could potentially be vibrations of tiny strings that extend into these extra dimensions. These higher dimensional interactions could explain why dark matter seems to interact so weakly with ordinary matter, as its effects might be spread across dimensions we cannot directly observe. Another intriguing intersection comes from the idea of brane worlds, where our observable universe exists on a three-dimensional membrane or brane floating in a higher dimensional space. In some of these models, dark matter could be ordinary matter trapped on a parallel brane, explaining its gravitational influence on our visible universe while accounting for its apparent invisibility. These higher dimensional approaches to dark matter offer potential solutions to long-standing puzzles in cosmology. They could help explain the exact abundance of dark matter in the universe, its distribution in galactic halos, and even its role in the formation of large-scale structures. As dark matter detectors become more sensitive and particle accelerators probe higher energies, Scientists hope to find evidence that could support or refute these higher dimensional theories, potentially revolutionizing our view of the cosmos and the hidden forces that shape it. Several mathematical frameworks point to the possibility of higher dimensions beyond the three spatial dimensions and one time dimension we experience in our everyday lives. String theory, a prominent candidate for a unified theory of physics, requires 10 or 11 dimensions to function mathematically. These extra dimensions are thought to be tightly curled up and imperceptible at our scale, but their existence is crucial for the theory's consistency. Another mathematical concept suggesting higher dimensions is the Kaluza-Klein theory. This theory attempts to unify gravity with electromagnetism by introducing a fifth dimension. While not fully successful, it demonstrates how additional dimensions could potentially explain fundamental forces in our universe. Mathematicians have also explored higher dimensional analogues of familiar objects. The study of four-dimensional polytopies, for instance, reveals complex geometric structures that can only exist in higher dimensions. These mathematical constructs, while abstract, hint at the rich possibilities that additional dimensions could offer. Quantum mechanics, too, indirectly supports the idea of higher dimensions. The mathematical formalism of quantum theory often involves multidimensional Hilbert spaces, suggesting that reality at its most fundamental level might be more complex than our three-dimensional perception allows us to see. Quantum mechanics experiments have revealed intriguing phenomena that challenge our understanding of reality and suggest the possibility of additional dimensions beyond the three spatial dimensions and one time dimension we experience in our everyday lives. One of the most compelling pieces of evidence comes from the bizarre behavior of quantum particles in experiments like the double-slit experiment. In the double-slit experiment, individual particles such as electrons or photons are fired at a screen with two narrow slits. Classical physics predicts these particles should create two distinct bands on a detector behind the slits. However, what scientists observe is an interference pattern, as if the particle had gone through both slits simultaneously and interfered with itself. This suggests that particles exist in multiple states or positions at once, a phenomenon known as quantum superposition. Some theoretical physicists propose that this seemingly impossible behavior could be explained if particles are able to interact with or move through additional spatial dimensions that we cannot directly observe. These extra dimensions might allow particles to take shortcuts or exist in multiple states that appear contradictory from our limited four-dimensional perspective. Furthermore, the concept of quantum entanglement, where particles can be instantaneously correlated regardless of the distance between them, has led some researchers to speculate about hidden dimensions. These extra dimensions could potentially provide a framework for understanding how information or influence can seem to travel faster than light without violating the principles of relativity. While these ideas remain highly speculative, they demonstrate how quantum mechanics continues to push the boundaries of our understanding of reality and the structure of the universe. Higher dimensions play a crucial role in theoretical physics, particularly in attempts to unify the fundamental forces of nature. These additional spatial dimensions beyond the three we experience in everyday life offer a potential framework for reconciling gravity with the other fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force. String theory, a leading candidate for a unified theory of physics, proposes that our universe actually contains 10 or 11 dimensions. In this model, the extra dimensions are thought to be tightly curled up and incredibly small, explaining why we don't perceive them directly. These compact dimensions could provide the necessary mathematical space for gravity to interact with the other forces on equal footing. The concept of higher dimensions allows for a more elegant and symmetrical description of particle physics. It provides a way to explain the seemingly arbitrary properties of particles, such as their masses and charges, as consequences of how strings vibrate in these extra dimensions. This approach offers a potential solution to long-standing puzzles in physics, including the hierarchy problem and the nature of dark matter. While the existence of higher dimensions remains hypothetical, their theoretical implications continue to drive research in particle physics and cosmology. Scientists are exploring ways to detect indirect evidence of these extra dimensions, which could revolutionize our understanding of the universe and bring us closer to a unified theory of everything. Supersymmetry and higher dimensions are both intriguing concepts in theoretical physics that push the boundaries of our understanding of the universe. Supersymmetry proposes a fundamental symmetry between two types of particles, bosons and fermions. This theory suggests that every known particle has a supersymmetric partner with similar properties but different spin. The connection between supersymmetry and higher dimensions becomes apparent when we consider string theory, a framework that attempts to unify all fundamental forces. String theory requires extra spatial dimensions beyond the three we experience in everyday life. These additional dimensions could provide the necessary space for supersymmetric particles to exist. In some versions of string theory, supersymmetry is a natural consequence of these extra dimensions. The idea is that as we move into higher dimensions, new symmetries emerge, including the symmetry between bosons and fermions. This relationship suggests that the extra dimensions might be crucial for explaining why our universe appears to have the properties it does. While both supersymmetry and higher dimensions remain theoretical, they offer tantalizing possibilities for understanding the fundamental nature of reality. Scientists continue to search for evidence of supersymmetric particles and signs of extra dimensions, hoping to unlock new insights into the fabric of the cosmos. The holographic principle is a fascinating concept in theoretical physics that suggests our three-dimensional reality might be an illusion. It proposes that all the information contained in a volume of space can be described on a two-dimensional boundary of that region. This idea draws an intriguing parallel between the universe and a hologram, where a three-dimensional image is encoded on a two-dimensional surface. This principle has profound implications for our understanding of dimensions and the nature of reality itself. It challenges our intuitive perception of space and suggests that what we experience as three-dimensional might be a projection of information stored on a lower dimensional surface. It implies that the universe could be like a giant hologram, with our three-dimensional world emerging from a two-dimensional cosmic surface. The holographic principle connects to dimensions by blurring the lines between what we perceive as distinct spatial dimensions. It suggests that the information content of any region of space can be entirely described by the information on its boundary. This idea has far-reaching consequences for theories of quantum gravity and our understanding of black holes. Moreover, the holographic principle has sparked new approaches to understanding the cosmos. It has led physicists to explore the possibility that our entire universe might be a holographic projection of information stored on a distant two-dimensional surface. This concept continues to inspire new research and push the boundaries of our understanding of space, time, and the fundamental nature of reality. Higher dimensions play a crucial role in theories of quantum gravity, extending our understanding beyond the familiar four dimensions of space and time. String theory, a prominent contender in the quest to unify quantum mechanics and general relativity, proposes that our universe actually contains 10 or 11 dimensions. These extra dimensions, according to string theory, are tightly curled up and exist at scales far smaller than we can currently observe. They provide the necessary mathematical framework to describe the fundamental particles and forces of nature as vibrating strings or membranes. By incorporating these additional dimensions, string theory attempts to resolve the incompatibilities between quantum mechanics and gravity. Another approach, known as loop quantum gravity, does not necessarily require extra dimensions, but reframes our concept of space and time at the quantum level. It suggests that space itself is composed of discrete units, like atoms of geometry, which become apparent only at the smallest scales. These theories of quantum gravity, with their incorporation of higher dimensions or novel spatial concepts, aim to provide a unified description of all fundamental forces and particles. They offer potential explanations for phenomena such as dark matter, dark energy, and the nature of black holes, pushing our understanding of the universe to new frontiers. Calabi-Yau manifolds play a crucial role in string theory, serving as the foundation for understanding the hidden dimensions of our universe. These complex mathematical structures are named after mathematicians Eugenio Calabi and Xingtung Yau, who made significant contributions to their study. In string theory, our universe is thought to consist of 10 or 11 dimensions, far more than the 4 we can directly observe. The extra dimensions are believed to be curled up into tiny, intricate shapes that are imperceptible to us. These shapes are represented by Calabi-Yau manifolds, which provide a way to describe and analyze these hidden dimensions. The specific configuration of a Calabi-Yau manifold is thought to determine many of the fundamental properties of our universe, including the types of particles that exist and the forces that govern their interactions. Different Calabi-Yau shapes could potentially give rise to entirely different universes with their own unique laws of physics. Understanding Calabi-Yau manifolds is essential for string theorists as they attempt to unify quantum mechanics and general relativity, potentially providing a unified theory of everything. While these structures remain theoretical, they offer a tantalizing glimpse into the possible underlying fabric of reality, pushing the boundaries of our understanding of the cosmos and its fundamental nature. The hierarchy problem in physics deals with the vast difference between the strength of gravity and the other fundamental forces. This disparity has puzzled scientists for decades, as gravity appears to be much weaker than expected when compared to the electromagnetic, strong, and weak nuclear forces. Extra dimensions offer a potential solution to this conundrum by suggesting that gravity might not be as weak as we perceive it to be in our three-dimensional world. According to theories involving extra dimensions, gravity could be just as strong as the other forces, but most of its strength is leaking into these hidden dimensions. This means that we only experience a fraction of gravity's true power in our observable universe. The idea is that while other forces are confined to our 3 spatial dimensions, gravity can spread out across all dimensions, including the extra ones we cannot directly observe. These extra dimensions are theorized to be incredibly small and curled up, making them undetectable through our current methods of observation. They could exist at scales smaller than an atomic nucleus, which explains why we have not yet been able to detect them directly. By allowing gravity to operate in these additional dimensions, the theory potentially reconciles the apparent weakness of gravity with the strength of other fundamental forces. If proven correct, this concept could revolutionize our understanding of the universe and potentially unify gravity with the other fundamental forces, a goal that has eluded physicists for generations. However, it is important to note that while extra dimensions provide an elegant theoretical solution to the hierarchy problem, experimental evidence for their existence remains elusive, and research in this area continues to be a subject of intense scientific inquiry. Brain theory is a fascinating concept in theoretical physics that expands our understanding of the universe beyond the familiar 3 spatial dimensions and 1 dimension of time. The term brain is short for membrane, and it suggests that our entire universe might be a 3-dimensional membrane floating in a higher dimensional space. According to this theory, our universe could be just one of many brains existing in a larger multiverse. These brains might be separated by incredibly small distances in higher dimensions that we cannot perceive. This idea helps explain why gravity appears weaker than other fundamental forces, as it might be spread out across these extra dimensions. Brain theory relates to higher dimensions by proposing that while we are confined to our 3-dimensional brain, gravity and possibly other forces can interact across these extra dimensions. This could potentially explain certain mysteries in physics, such as the nature of dark matter or the apparent weakness of gravity compared to other fundamental forces. The concept of brains and higher dimensions challenges our everyday perception of reality and opens up new possibilities for understanding the cosmos. It suggests that what we consider to be the entire universe might be just a small part of a much larger, more complex structure existing in dimensions beyond our direct experience. Higher dimensions play a crucial role in many theories of the multiverse, expanding our understanding of reality beyond the familiar three spatial dimensions and one dimension of time. String theory, a prominent framework in theoretical physics, proposes that our universe might have as many as 10 or 11 dimensions. Most of these extra dimensions are thought to be tightly curled up and invisible to us, existing at scales far smaller than atoms. These additional dimensions provide the foundation for various multiverse concepts. In the brain multiverse theory, our observable universe exists on a three-dimensional membrane, or brain, floating in a higher dimensional space. Other universes might exist on parallel brains, separated from us by these extra dimensions. This could explain why gravity appears weaker than other fundamental forces, as it might be the only force able to travel between brains, spreading its influence across the higher dimensional space. Another multiverse model, the many worlds interpretation of quantum mechanics, doesn't necessarily require extra spatial dimensions, but instead proposes that every quantum event creates new timeline branches, effectively spawning new universes. While not explicitly tied to higher dimensions, this interpretation aligns with the idea of a reality more complex than our everyday experience suggests. The concept of higher dimensions in multiverse theories challenges our intuition and pushes the boundaries of what we consider possible. It offers potential explanations for fundamental questions about the nature of our universe and opens up new avenues for exploring the cosmos beyond our observable realm. As we continue to develop more sophisticated mathematical models and observational techniques, these higher dimensional concepts may provide key insights into the fundamental structure of reality. Higher dimensions fundamentally alter our understanding of reality by expanding the boundaries of what we can conceive. Our everyday experience is limited to three spatial dimensions and one dimension of time, but mathematics and theoretical physics suggest the existence of additional dimensions beyond these four. These extra dimensions challenge our perception because they exist outside the realm of our direct sensory experience. We cannot see, touch, or interact with them in the same way we do with the familiar dimensions of length, width, and height. This limitation of our senses makes it difficult for us to truly grasp the nature of higher dimensional space. Imagine a two-dimensional being living on a flat surface, unable to perceive depth. Such a being would struggle to understand our three-dimensional world, just as we struggle to comprehend higher dimensions. These additional dimensions could potentially explain phenomena that seem mysterious or impossible within our current framework, such as quantum entanglement or the nature of dark matter. The concept of higher dimensions also challenges our notions of cause and effect, time, and the very fabric of the universe. It suggests that what we perceive as our entire reality might be just a small slice of a much larger, more complex cosmic structure. This idea pushes the boundaries of our imagination and forces us to reconsider the nature of existence itself. The concept of higher dimensions challenges our understanding of reality and sparks profound philosophical inquiries. One key question is whether our perception of the universe is fundamentally limited by our ability to directly experience only three spatial dimensions and time. This leads us to ponder if there are aspects of existence that lie forever beyond our comprehension. Another intriguing philosophical consideration is the nature of consciousness and its potential relationship to higher dimensions. Some theorists propose that our conscious experiences might be influenced by or even originate from higher dimensional realms, raising questions about the true nature of human awareness and our place in the cosmos. The possibility of higher dimensions also prompts us to reconsider our notions of causality and free will. If events in our three-dimensional world are influenced by forces or entities in higher dimensions, it could challenge our understanding of cause and effect and the degree of control we have over our actions and decisions. Furthermore, the existence of higher dimensions raises questions about the fundamental nature of reality itself. Are the laws of physics as we know them complete, or are they merely shadows of more complex principles operating in higher dimensional spaces? This line of inquiry pushes us to examine the limits of scientific knowledge and the ultimate nature of truth in our universe. The concept of higher dimensions opens up intriguing possibilities for our understanding of free will. In our familiar three-dimensional space plus time, the notion of cause and effect seems straightforward. However, if we consider the existence of higher dimensions beyond what we can directly observe, our perspective on free will could dramatically shift. In higher dimensional models, events that appear separate and unconnected in our limited view might be intimately linked when seen from a higher dimensional perspective. This could mean that choices we perceive as free and independent might actually be part of a larger, predetermined pattern that only becomes apparent when viewed from these additional dimensions. Some theories suggest that our consciousness might extend into these higher dimensions, potentially allowing for decision-making processes that transcend our current understanding of physics and neuroscience. This could provide a new framework for understanding free will, where our choices are influenced by factors outside our conventional perception of reality. Higher dimensions fundamentally reshape our understanding of causality, challenging the linear cause and effect relationships we observe in our three-dimensional world. In higher dimensional spaces, events that appear disconnected or even impossible in our reality might be naturally linked. Consider how a two-dimensional being would perceive a three-dimensional object passing through their plane. They would see seemingly unconnected shapes appear, change, and disappear without apparent cause. Similarly, in higher dimensions, what we perceive as separate events could be part of a single, unified phenomenon. These additional dimensions could allow for connections between distant points in space and time that are imperceptible to us. This concept has profound implications for our understanding of physics, potentially explaining phenomena like quantum entanglement or providing new perspectives on the nature of time itself. Moreover, higher dimensions might introduce new forms of causality that operate outside our conventional framework. Events could influence each other through these hidden dimensions, creating causal relationships that seem to defy our current laws of physics. This possibility opens up exciting avenues for theoretical physics and cosmology, pushing the boundaries of our understanding of the universe and its fundamental workings. Higher dimensions in physics and mathematics offer intriguing connections to philosophical concepts of determinism. These additional spatial or temporal dimensions beyond our familiar three spatial dimensions and one time dimension could potentially contain information about all possible outcomes and events in our universe. In a higher dimensional framework, our perceived reality might be a slice or projection of a larger, more complex structure. This idea aligns with some interpretations of determinism, suggesting that all events and choices are predetermined by prior causes in a grand cosmic design. The higher dimensions could theoretically encode all possible paths and outcomes, with our observable universe representing just one trajectory through this vast landscape of possibilities. Some theories propose that quantum phenomena, which appear random and indeterministic in our four-dimensional perspective, might be fully deterministic when viewed from higher dimensions. This concept challenges our understanding of free will and causality, as it implies that apparent randomness or choice might be an illusion arising from our limited perception of reality. However, it is crucial to note that these ideas remain largely speculative and philosophical. While higher dimensional models provide valuable mathematical tools in physics, their relation to determinism and the nature of reality continues to be a subject of debate among scientists and philosophers alike. the concept of higher dimensions opens up intriguing possibilities for our understanding of consciousness. While our everyday experience is limited to 3 spatial dimensions and 1 temporal dimension, theoretical physics suggests the potential existence of additional dimensions beyond our perception. These higher dimensions could provide a framework for explaining aspects of consciousness that currently elude our scientific understanding. For instance, the hard problem of consciousness, which questions how subjective experiences arise from physical processes in the brain, might find new avenues for exploration in higher dimensional models. Some theories propose that consciousness itself could be a higher dimensional phenomenon, with our 3-dimensional brains acting as receivers or interpreters of this information. This perspective aligns with certain philosophical and spiritual traditions that view consciousness as fundamental to the universe rather than an emergent property of complex biological systems. Moreover, higher dimensions could offer explanations for phenomena like near-death experiences, altered states of consciousness, and the sense of unity reported in deep meditative states. While these ideas remain speculative, they highlight how expanding our dimensional understanding might revolutionize our approach to the enigma of consciousness, potentially bridging the gap between scientific materialism and subjective experience. The concept of higher dimensions has intrigued scientists and philosophers for centuries, echoing ancient ideas about the nature of reality. Many ancient philosophical traditions, from Greek to Eastern thought, explored the notion that our perceived world might be just a fraction of a larger, more complex reality. Plato's allegory of the cave, for instance, presents a view of reality that resonates with modern concepts of higher dimensions. In this allegory, people chained in a cave see only shadows on a wall, mistaking these 2-dimensional projections for the entirety of existence. This bears a striking similarity to how we, as 3-dimensional beings, might perceive shadows of higher dimensional objects. In Eastern philosophy, particularly in some schools of Buddhism and Hinduism, the concept of multiple realms of existence aligns with the idea of higher dimensions. These traditions often speak of various planes of reality beyond our immediate perception, much like how string theory in modern physics proposes extra dimensions beyond the 4 we commonly experience. The ancient mystical tradition of Kabbalah also presents a multi-layered model of reality, with different levels of existence interconnected in complex ways. This hierarchical structure of reality shares conceptual similarities with how modern physicists describe the potential relationships between dimensions. These parallels highlight how ancient intuitions about the nature of reality continue to find expression in contemporary scientific exploration of higher dimensions. The potential existence of higher dimensions raises profound ethical questions that challenge our understanding of reality and morality. If entities or forces from higher dimensions can influence our universe, we must grapple with the implications for free will and determinism. Are our actions truly our own, or are they subtly guided by higher dimensional influences beyond our perception? This possibility also brings into question the nature of responsibility and accountability. If higher dimensional beings can affect our world, to what extent are they responsible for the consequences of their actions in our reality? Conversely, how does this impact our own sense of moral responsibility if our choices are potentially influenced by forces we cannot comprehend? The concept of higher dimensional influence also raises concerns about privacy and autonomy. If beings from other dimensions can observe or interact with our universe in ways we cannot detect, it challenges our notions of personal space and freedom. This scenario could be seen as a cosmic version of surveillance, where our entire existence might be open to observation or manipulation by entities beyond our dimensional boundaries. Furthermore, the ethical implications extend to how we, as a species, should respond to the possibility of higher dimensional influence. Should we actively seek to understand and potentially communicate with these higher dimensional entities? Or would such attempts be fraught with danger, potentially exposing our universe to unforeseen risks? These questions force us to reconsider our place in the cosmos and the ethical frameworks that guide our actions in an increasingly complex and mysterious universe. Higher dimensional concepts have profoundly shaped both literature and science fiction, sparking the imagination of writers and readers alike. These ideas have allowed authors to explore complex scientific theories while crafting captivating narratives that challenge our perceptions of reality. In literature, works like Edwin Abbott's Flatland introduced readers to the concept of dimensions beyond our familiar three. This novella uses a two-dimensional world to explain how higher dimensions might interact with lower ones, serving as both a mathematical exploration and a social satire. Other authors, such as H.G. Wells in The Time Machine, incorporated the idea of time as a fourth dimension, paving the way for countless time travel stories. Science fiction has embraced higher dimensional concepts with particular enthusiasm. Writers like Isaac Asimov and Arthur C. Clarke have used these ideas to create mind-bending plots involving parallel universes and alternate realities. The notion of hypercubes and tesseracts has appeared in works ranging from Madeleine L'Englei's A Wrinkle in Time to Marvel's cinematic universe, offering a way to visualize and traverse vast cosmic distances. These literary explorations have not only entertained, but also helped popularize scientific theories. They have made complex ideas more accessible to the general public, fostering interest in fields like theoretical physics and cosmology. In turn, scientific advancements in string theory and multiverse concepts continue to fuel new stories, creating a symbiotic relationship between science and fiction that pushes the boundaries of our imagination. Many science fiction films and television series have delved into the concept of higher dimensions, captivating audiences with mind-bending ideas about reality beyond our familiar three-dimensional world. The critically acclaimed movie Interstellar, directed by Christopher Nolan, explored higher dimensions as a key plot element, depicting a mysterious tesseract where time became a physical dimension that could be traversed. Another notable example is the long-running British television series Doctor Who, which frequently features interdimensional travel and beings from higher dimensions. The TARDIS, the iconic time machine in the show, is famously described as being bigger on the inside, hinting at its multidimensional nature. The Marvel Cinematic Universe has also incorporated higher dimensions in its storytelling. In Doctor Strange, the titular character learns to manipulate reality by tapping into other dimensions visualized through kaleidoscopic special effects. Similarly, the animated film Spider-Man Into the Spider-Verse playfully explores the idea of parallel universes existing in different dimensions. These popular media representations have helped bring complex scientific concepts to a wider audience, sparking curiosity about the nature of our universe and the possibility of realities beyond our immediate perception. While often taking creative liberties, these shows and movies have played a crucial role in popularizing discussions about higher dimensions and multiverse theories. Artists have long been fascinated by the concept of higher dimensions, striving to capture these abstract ideas in visual form. In the early 20th century, Cubist painters like Pablo Picasso experimented with depicting multiple perspectives of an object simultaneously on a two-dimensional canvas, hinting at a fourth spatial dimension. This technique allowed viewers to see different sides of a subject at once, challenging traditional notions of space and time. Some artists have used geometric forms and intricate patterns to suggest higher dimensional spaces. For instance, Dutch artist M.C. Escher created mind-bending lithographs and woodcuts that play with impossible geometries and spatial paradoxes. His works often feature structures that could only exist in higher dimensions, forcing viewers to grapple with concepts beyond our everyday three-dimensional experience. In more recent years, digital artists have leveraged computer graphics to create immersive representations of higher dimensional objects. By using techniques like slicing and projection, they can generate three-dimensional shadows of four-dimensional shapes allowing viewers to interact with and explore these otherworldly forms. These digital creations often resemble complex, shifting structures that defy our usual understanding of space. Conceptual artists have also tackled higher dimensions through more abstract means. Some use mathematical concepts as inspiration, creating installations or sculptures that embody ideas from string theory or quantum mechanics. Others focus on the philosophical implications of higher dimensions, using their art to explore questions of perception, reality, and the limits of human understanding. Higher dimensional theories have profoundly influenced religious and spiritual beliefs, challenging traditional concepts of reality and existence. These theories, which suggest the universe may contain more dimensions than the four we commonly experience, have sparked new ways of thinking about the nature of God, the soul, and the afterlife. For many, the idea of higher dimensions has provided a scientific framework to explain spiritual concepts. Some believers see these additional dimensions as potential realms for spiritual entities or the afterlife, bridging the gap between scientific understanding and religious faith. This has led to reinterpretations of sacred texts and religious doctrines, with some arguing that ancient spiritual insights might have been early intuitions about the multidimensional nature of reality. Conversely, these theories have also reinforced skepticism in some circles. Critics argue that invoking higher dimensions to explain religious phenomena is simply replacing one unknown with another. They contend that such theories do not provide concrete evidence for spiritual claims and may instead be used to justify unfalsifiable beliefs. Ultimately, higher dimensional theories have stimulated dialogue between science and spirituality, encouraging both believers and non-believers to reconsider their understanding of the universe and our place within it. This ongoing conversation continues to shape modern spiritual thought and scientific inquiry, blurring the lines between the physical and the metaphysical in ways that were unimaginable just a century ago. The concept of higher dimensions has sparked fascinating explorations in music and sound art, pushing creators to think beyond traditional three-dimensional space. Musicians and sound artists have drawn inspiration from theoretical physics and mathematics to craft innovative compositions that challenge our auditory perceptions. One approach involves creating soundscapes that attempt to represent or evoke the idea of higher dimensions. Composers use complex layering techniques, intricate spatial audio, and unconventional harmonies to create sonic environments that feel expansive and otherworldly. These pieces often aim to give listeners a sense of experiencing something beyond our typical three-dimensional reality. Some artists have developed new instruments or modified existing ones to produce sounds that seem to transcend normal spatial limitations. For example, certain electronic music producers use algorithms based on higher dimensional mathematics to generate unique tones and rhythms. Others employ advanced speaker systems to create immersive audio experiences that surround the audience, blurring the lines between different spatial planes. The influence of higher dimensions has also led to the creation of conceptual works that explore the relationship between sound, space, and time. These pieces often incorporate visual elements or interactive components, inviting audiences to engage with the music in ways that challenge their perception of reality and dimensionality. By pushing the boundaries of what we consider possible in sound and music, artists continue to expand our understanding of the universe and our place within it. Higher dimensions have become a fascinating playground for digital artists and virtual reality creators, pushing the boundaries of what we can perceive and experience. In the realm of contemporary digital art, artists are exploring concepts beyond our familiar three-dimensional world, incorporating ideas from theoretical physics and mathematics to create mind-bending visual experiences. Digital artists use software and algorithms to generate artworks that simulate or represent higher dimensional spaces. These creations often feature impossible geometries, non-Euclidean structures, and visual paradoxes that challenge our perception of reality. By manipulating perspective, color, and form in ways that defy conventional physics, Artists can give viewers a glimpse into worlds that exist only in abstract mathematical concepts. Virtual reality takes this exploration of higher dimensions to new levels by immersing users in fully realized digital environments. VR developers are creating experiences that allow people to interact with and navigate through simulated higher dimensional spaces. These virtual worlds can bend and warp in ways that would be impossible in physical reality, giving users a visceral sense of what it might be like to exist in a universe with more than 3 spatial dimensions. The intersection of higher dimensions, digital art, and virtual reality is not just about creating visually stunning experiences. It also serves as a powerful tool for scientific visualization and education. Complex mathematical and physical concepts that are difficult to grasp in traditional formats can be rendered in interactive, immersive environments, making abstract ideas more tangible and accessible to a wider audience. Video game designers have embraced higher dimensional concepts to create innovative and mind-bending gameplay experiences. These abstract mathematical ideas have opened up new possibilities for level design, puzzle mechanics, and storytelling in games. One notable example is the game Miegakure, which allows players to navigate a 4-dimensional world. By shifting between 3-dimensional cross-sections of this higher dimensional space, players can solve puzzles and traverse obstacles that would be impossible in our familiar 3-dimensional reality. This game gives players a tangible way to interact with and visualize 4th-dimensional concepts. Other games have used the idea of parallel universes or alternate dimensions as core gameplay elements. Titles like Portal and Antechamber challenge players to think beyond traditional spatial reasoning, using interconnected portals or non-Euclidean geometry to create seemingly impossible architectural spaces. These designs force players to rewire their understanding of space and navigation. Some puzzle games incorporate tesseracts, hypercubes, and other higher dimensional objects as part of their challenges. By manipulating these complex shapes, players gain insight into how objects might behave in higher dimensions, bridging the gap between abstract mathematical concepts and interactive experiences. Many people mistakenly believe that higher dimensions are mystical realms or parallel universes we could potentially visit. This idea, while captivating for science fiction, is not accurate from a scientific standpoint. In reality, dimensions are mathematical concepts used to describe the properties of space and time. Another common misconception is that the 4th dimension is time. While time is often referred to as the 4th dimension in physics, it is fundamentally different from spatial dimensions. In mathematics, the 4th dimension is simply another spatial direction perpendicular to the 3 we experience. Some incorrectly think that beings living in higher dimensions would be godlike, able to see and manipulate our 3-dimensional world at will. This notion stems from a misunderstanding of how dimensional relationships work. A 4-dimensional being would not necessarily perceive our world any differently than we do. Lastly, there is a widespread belief that string theory proves the existence of higher dimensions. While string theory does propose extra dimensions, these are typically thought to be extremely small and curled up, not vast expanses we could explore. These misconceptions highlight the challenge of accurately conveying complex scientific concepts to the public. The concept of higher dimensions influencing our 3-dimensional reality is a fascinating area of theoretical physics. While we cannot directly observe or interact with higher dimensions, their potential effects on our universe could be profound and far-reaching. One way a higher dimension might exert control over our space is through gravitational influence. Some theories suggest that gravity, unlike other fundamental forces, might be able to propagate through extra dimensions. This could explain why gravity appears weaker than other forces in our 3-dimensional world, as its effects might be spread across multiple dimensions. Another possibility is that higher dimensions could contain vast amounts of energy or exotic matter that shapes the structure and behavior of our universe. These hidden dimensions might influence the distribution of dark matter and dark energy, which together make up about 95% of the known universe. Their effects could be responsible for the accelerating expansion of space and the formation of large-scale cosmic structures. Some scientists speculate that higher dimensions might even allow for alternate versions of our universe to exist simultaneously. In this scenario, events in our three-dimensional space could be influenced by interactions with these parallel realities, potentially explaining quantum phenomena or other mysterious aspects of our world that currently defy conventional explanation. The concept of higher dimensions influencing our universe has intrigued physicists and cosmologists for decades. String theory, a prominent framework in theoretical physics, suggests that our universe might actually consist of 10 or 11 dimensions, most of which are imperceptible to us. These extra dimensions could potentially explain several fundamental aspects of our physical reality. One area where higher dimensions might play a role is gravity. The apparent weakness of gravity compared to other fundamental forces has long puzzled scientists. Some theories propose that gravity might be leaking into other dimensions, explaining why it appears so weak in our three-dimensional space. This could help reconcile gravity with quantum mechanics, a long-standing challenge in physics. Another intriguing possibility is that higher dimensions might explain the nature of dark matter and dark energy. These mysterious components, which seem to make up the majority of our universe, could potentially be manifestations of extra-dimensional effects. Some researchers speculate that particles from higher dimensions might be interacting with our universe, creating the gravitational effects we attribute to dark matter. Quantum entanglement, a phenomenon where particles can instantaneously influence each other regardless of distance, might also have roots in higher dimensions. Some theories suggest that entangled particles could be connected through higher dimensional space, providing a potential explanation for this seemingly impossible, faster-than-light communication. Higher dimensions could profoundly influence the distribution of matter in our universe, reshaping our understanding of cosmic structure. These additional spatial dimensions, beyond the three we experience, might act as hidden conduits for gravitational forces, altering how matter clumps together on large scales. In a higher dimensional universe, gravity could potentially spread out or disperse more rapidly than in our observable three-dimensional space. This would lead to weaker gravitational attraction between distant objects, potentially explaining why galaxies appear to be moving apart faster than current models predict. The extra dimensions might also provide pathways for matter to accumulate in ways we cannot directly observe, leading to apparent voids or unexplained concentrations in our visible cosmos. Furthermore, these higher dimensions could allow for the existence of structures and patterns in matter distribution that are invisible to us, much like how a two-dimensional being would be unable to perceive depth. This could account for some of the mysterious dark matter that scientists believe makes up a significant portion of our universe. The influence of higher dimensions might create gravitational effects that we attribute to unseen matter, when in reality it is the geometry of space itself causing these phenomena. The concept of higher dimensions affecting matter distribution also ties into string theory, which proposes that the fundamental constituents of the universe are tiny vibrating strings existing in multiple dimensions. If true, the way these strings interact across higher dimensions could have far-reaching consequences for how matter is organized throughout the cosmos, potentially explaining the intricate web-like structure we observe in the large-scale distribution of galaxies. Higher dimensions could play a crucial role in the expansion of the universe, offering potential explanations for cosmic phenomena that challenge our current understanding. These extra dimensions, beyond the three spatial dimensions and one time dimension we experience, might provide the underlying framework for the universe's expansion. String theory, a leading candidate for a unified theory of physics, proposes that our universe could have up to 11 dimensions. These additional dimensions might be compactified or curled up so tightly that they are undetectable in our everyday experience. However, they could still exert significant influence on the large-scale behavior of the cosmos. One intriguing possibility is that the expansion of the universe is driven by the properties of these higher dimensions. As our three-dimensional space expands, it might be moving through or interacting with these extra dimensions in ways we cannot directly observe. This interaction could be the source of the mysterious dark energy that appears to be accelerating the universe's expansion. Furthermore, the concept of brains from string theory suggests our universe might be a three-dimensional membrane floating in a higher dimensional space. The movement or interaction of these brains could potentially explain the expansion we observe, providing a new perspective on the nature of cosmic inflation and the Big Bang itself. Higher dimensions could profoundly affect subatomic particles in ways that challenge our understanding of physics. These extra dimensions, beyond the familiar three spatial dimensions and one of time, might provide new pathways for particles to interact or move. In string theory, for instance, subatomic particles are thought to be tiny vibrating strings existing in 10 or 11 dimensions. Most of these dimensions are believed to be curled up so tightly that we cannot directly observe them. However, their presence could explain some of the puzzling behaviors we see in quantum mechanics. These extra dimensions might allow particles to take shortcuts through space-time, potentially explaining phenomena like quantum entanglement, where particles can influence each other instantaneously across vast distances. They could also account for the apparent weakness of gravity compared to other fundamental forces, as gravity might be spread out across all dimensions, while other forces are confined to our observable four-dimensional space-time. Furthermore, the existence of higher dimensions could provide new avenues for particle interactions, potentially giving rise to yet undiscovered particles or forces. This could have far-reaching implications for our understanding of dark matter, dark energy, and the fundamental nature of the universe itself. The concept of higher dimensions opens up fascinating possibilities for our understanding of time. In our familiar three-dimensional space, time appears to flow in one direction. However, if we consider the existence of higher dimensions beyond what we can directly observe, the nature of time could be fundamentally different. In higher dimensions, time might not be limited to a single linear progression. Instead, it could exist as a multi-dimensional construct, allowing for multiple timelines or even the simultaneous existence of past, present, and future. This could potentially explain phenomena like quantum entanglement, where particles appear to communicate instantly across vast distances, seemingly defying our conventional understanding of cause and effect. Moreover, higher dimensions might allow for the existence of closed time-like curves, theoretical paths through space-time that return to their starting point. This could theoretically enable time travel or the ability to view events from different temporal perspectives. While this remains highly speculative, it highlights how our perception of time could be limited by our inability to directly experience higher dimensions. The impact of higher dimensions on time could also have profound implications for the structure and evolution of our universe. It might provide new insights into the nature of dark energy, the mysterious force driving the accelerating expansion of the cosmos, or offer alternative explanations for the apparent arrow of time we observe. As we continue to explore these concepts, we may need to radically reshape our understanding of time and its role in shaping reality. The concept of higher dimensions opens up fascinating possibilities for understanding the fundamental forces of nature. In our familiar three-dimensional space, we observe four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. However, the existence of additional spatial dimensions could dramatically alter how these forces operate and interact. One intriguing idea is that gravity might actually be as strong as the other fundamental forces, but most of its strength is leaking into higher dimensions. This could explain why gravity appears so weak compared to the other forces in our three-dimensional world. If we could access or manipulate these higher dimensions, we might be able to harness the full strength of gravity, potentially revolutionizing our understanding of physics and enabling new technologies. Higher dimensions could also provide a framework for unifying the fundamental forces. String theory, for instance, proposes that our universe actually has 10 or 11 dimensions, with most of them curled up so small that we cannot detect them. In this model, the different fundamental forces we observe might be various manifestations of a single, unified force operating across all dimensions. Furthermore, the behavior of particles and forces in higher dimensions could lead to unexpected phenomena. For example, particles might be able to take shortcuts through higher dimensions, appearing to move faster than light from our three-dimensional perspective. This could have profound implications for our understanding of causality and the nature of space-time itself. Higher dimensions could profoundly influence the formation and evolution of galaxies in ways that extend beyond our current three-dimensional understanding of the universe. These additional spatial dimensions, if they exist, might provide explanations for some of the mysteries surrounding galactic behavior and cosmic structure. One intriguing possibility is that higher dimensions could affect the distribution of dark matter, which plays a crucial role in galaxy formation. Dark matter, invisible to our current detection methods, might interact with or move through these extra dimensions, influencing how it clusters and shapes the visible matter in galaxies. This could potentially explain some of the unexpected dark matter distributions observed in certain galaxies. Moreover, higher dimensions might impact the way gravity works on cosmic scales. In some theories, gravity could be stronger or behave differently in these extra dimensions, which could account for the rapid formation of early galaxies or the unexpected rotational speeds of stars in galactic outskirts. This could provide an alternative explanation to dark matter for some galactic phenomena. Additionally, the existence of higher dimensions could influence the merging and interaction of galaxies. These cosmic collisions, which play a significant role in galactic evolution, might be affected by forces or matter distributions that extend into dimensions beyond our perception, potentially explaining some of the complex structures and behaviors observed in interacting galaxy systems. Scientists are employing several ingenious methods to search for evidence of higher dimensions beyond the four we can directly observe. One approach involves studying particle collisions at facilities like the Large Hadron Collider. Researchers analyze these high-energy collisions, looking for signs of particles or energy disappearing in ways that might indicate interactions with extra dimensions. Another method focuses on gravity, which is theorized to potentially spread into additional dimensions. Scientists are conducting precise measurements of gravitational forces at very small scales, searching for deviations from expected behavior that could suggest the presence of extra dimensions. Astronomers are also scrutinizing cosmic phenomena for clues. They examine the cosmic microwave background radiation, gravitational waves, and the large-scale structure of the universe for patterns or anomalies that might be explained by the existence of higher dimensions. Some researchers are exploring the possibility of detecting microscopic black holes, which could form more easily in a universe with extra dimensions. The detection of such objects would provide strong evidence for the existence of higher dimensions and potentially revolutionize our understanding of the cosmos. While higher dimensions exist beyond our direct perception, their effects might be subtly woven into the fabric of our reality. One intriguing possibility is through the behavior of fundamental particles. The peculiar properties of neutrinos, which seem to pass through normal matter with ease, could potentially be explained by their movement through higher dimensions. Gravity, often described as the weakest of the four fundamental forces, presents another potential window into higher dimensions. Some theories suggest that gravity might be as strong as the other forces, but its effects are spread across additional dimensions, making it appear weaker in our three-dimensional space. This could explain why gravity seems so feeble compared to electromagnetism or the strong nuclear force. String theory, a prominent candidate for a unified theory of physics, proposes that our universe might have as many as 10 or 11 dimensions. While we cannot directly observe these extra dimensions, they could manifest in the behavior of subatomic particles or in the properties of dark matter and dark energy, which together make up the majority of our universe's content. Even in our everyday lives, the mathematics of higher dimensions finds practical applications. From the algorithms that power our internet searches to the complex financial models used in global markets, the concepts of higher dimensional spaces play a crucial role. While we may not see these extra dimensions, their influence may be more pervasive than we realize, shaping the unseen foundations of our world. To better detect higher dimensions, scientists need to develop more sophisticated particle accelerators and detectors. These advanced machines would allow researchers to probe subatomic particles at even higher energies, potentially revealing evidence of extra dimensions. Improved gravitational wave detectors are also crucial. By increasing their sensitivity, we might detect gravitational waves from higher dimensional events, such as the collision of higher dimensional objects. This could provide indirect evidence for the existence of dimensions beyond our familiar 3 spatial dimensions and 1 time dimension. Quantum sensors represent another promising avenue. These devices, which exploit quantum mechanical properties, could potentially detect minute variations in physical constants or forces that might indicate the presence of hidden dimensions. Advancements in quantum computing could also aid in processing and analyzing the vast amounts of data generated by these experiments. Lastly, space-based experiments and observatories could offer new perspectives. By conducting experiments in the unique environment of space, free from Earth's interference, scientists might uncover subtle effects that point to the existence of higher dimensions. These technological advancements, working in concert, could bring us closer to understanding the true nature of our universe and its hidden dimensions. The Large Hadron Collider, located near Geneva, Switzerland, is a powerful tool in the quest to understand the fundamental nature of our universe. This massive particle accelerator could potentially help detect extra dimensions by creating conditions similar to those in the early universe, allowing scientists to probe the fabric of space and time at incredibly small scales. One way the Large Hadron Collider might detect extra dimensions is through the creation of microscopic black holes. According to some theories, if extra dimensions exist, gravity could be much stronger at very small distances. This increased strength might allow the collider to create tiny black holes that would quickly evaporate, leaving behind a distinctive pattern of particles. The detection of these particle patterns could provide evidence for the existence of extra dimensions. Another possibility involves the search for particles that could move into or interact with extra dimensions. Some theories suggest that certain particles, such as gravitons, might be able to travel through additional spatial dimensions. The Large Hadron Collider could potentially detect missing energy in collision events, which might indicate that particles have escaped into these hidden dimensions. The collider might also help scientists look for evidence of parallel universes predicted by some versions of string theory. By studying the properties of newly discovered particles or unusual energy distributions in collision events, researchers might find clues that point to the existence of other universes occupying additional dimensions alongside our own. Quantum computers hold immense potential for exploring higher dimensions in ways that classical computers simply cannot match. These advanced machines leverage the principles of quantum mechanics, allowing them to process vast amounts of information simultaneously and tackle complex problems that would take traditional computers an impractical amount of time to solve. In the realm of higher dimensions, quantum computers could revolutionize our understanding of string theory and M theory, which propose the existence of 10 or 11 dimensions respectively. These theories aim to unify our understanding of the fundamental forces of nature, but they involve mathematical models so complex that classical computers struggle to simulate them effectively. Quantum computers, with their ability to handle multidimensional calculations, could provide crucial insights into these extra dimensions and their implications for our universe. Furthermore, quantum computers could aid in simulating higher dimensional spaces and their properties. This capability could be instrumental in fields like topology and geometry, where understanding the nature of space itself becomes increasingly challenging as we move beyond the familiar three spatial dimensions. By creating quantum simulations of higher dimensional structures, scientists might uncover new mathematical relationships or physical principles that are difficult to perceive in our everyday three-dimensional experience. Additionally, quantum computers might help us explore the concept of quantum gravity, a theory that attempts to reconcile quantum mechanics with general relativity. This exploration often involves considering higher dimensional spaces, and quantum computers could provide the computational power needed to model these complex scenarios, potentially leading to breakthroughs in our understanding of the fundamental nature of space, time, and gravity. Gravitational wave detectors offer an exciting new avenue for exploring the possibility of higher dimensions in our universe. These sophisticated instruments, designed to detect ripples in the fabric of space-time, could potentially reveal subtle clues about the existence of dimensions beyond the four we commonly experience. One way gravitational wave detectors might contribute to identifying higher dimensions is by searching for unexpected patterns or anomalies in the signals they receive. If our universe has additional spatial dimensions, gravitational waves might behave differently than predicted by our current four-dimensional models. For instance, these waves could exhibit variations in strength or frequency that do not align with our standard understanding of gravity. Furthermore, gravitational wave detectors could potentially pick up signals from gravitational events occurring in higher dimensions. These events might produce distinctive signatures that stand out from the background noise, providing tantalizing evidence of a more complex cosmic structure. Scientists are particularly interested in looking for gravitational waves that seem to violate conservation of energy in our observable universe, as this could indicate energy leaking into or from hidden dimensions. Advanced gravitational wave detectors might also be able to probe the quantum nature of gravity, which some theories suggest is linked to the existence of higher dimensions. By pushing the boundaries of our observational capabilities, these instruments could help bridge the gap between quantum mechanics and general relativity, potentially uncovering new insights into the fundamental structure of reality and the role that extra dimensions might play in it. Several astronomical phenomena could potentially offer tantalizing hints of higher dimensions beyond the four we commonly experience. Black holes, those enigmatic cosmic objects with gravitational fields so intense that nothing can escape their grasp, might hold clues to extra dimensions. Some theories suggest that miniature black holes could serve as gateways to hidden dimensions, potentially allowing particles to escape our observable universe. Cosmic inflation, the rapid expansion of the universe in its earliest moments, presents another avenue for exploring higher dimensions. Certain models propose that this explosive growth was driven by the separation of extra dimensions from our familiar four-dimensional spacetime. If true, we might detect subtle imprints of this process in the cosmic microwave background radiation that permeates the universe. Dark matter and dark energy, mysterious components that make up the majority of the universe's mass and energy, could also be linked to higher dimensions. Some scientists speculate that these elusive substances might actually be manifestations of extra-spatial dimensions, explaining their apparent invisibility and peculiar effects on visible matter and cosmic expansion. Gravitational waves, ripples in the fabric of spacetime caused by cataclysmic cosmic events, offer yet another potential window into higher dimensions. Advanced detectors might one day pick up anomalies in these waves that could indicate the presence of extra dimensions influencing gravitational interactions across vast cosmic distances. Neutrino detectors are powerful tools in the quest to understand the fundamental nature of our universe, including the potential existence of extra dimensions. These elusive particles, which rarely interact with matter, could provide unique insights into realms beyond our familiar three spatial dimensions. One way neutrino detectors might aid in this search is by looking for anomalies in neutrino oscillations. As neutrinos travel through space, they change from one type to another. If extra dimensions exist, they could affect this oscillation pattern in ways that our current models do not predict. By precisely measuring these oscillations, scientists might detect subtle deviations that point to the influence of hidden dimensions. Another avenue of exploration involves studying the energy and direction of neutrinos from distant cosmic sources. If extra dimensions exist, they could cause neutrinos to take shortcuts through these additional spatial dimensions, arriving at Earth sooner than expected or from unexpected directions. Detecting such anomalies could provide evidence for the existence of extra dimensions and help scientists better understand their nature. Furthermore, neutrino detectors might help in the search for microscopic black holes. Some theories suggest that if extra dimensions exist, the energy required to create miniature black holes in particle colliders would be much lower than previously thought. Neutrino detectors could potentially observe the decay of these short-lived black holes, providing indirect evidence for extra dimensions and opening new avenues for understanding the structure of spacetime. Proving the existence of higher dimensions presents several significant challenges for scientists and researchers. One major obstacle is our limited sensory perception. Humans can directly observe and interact with only 3 spatial dimensions and 1 dimension of time. This inherent limitation makes it extremely difficult to detect or measure any additional dimensions that might exist beyond our everyday experience. Another hurdle is the lack of observable effects from higher dimensions at the scales we can currently probe. Many theories that propose extra dimensions suggest they are either extremely small, compactified, or somehow hidden from our normal interactions. This means that even our most advanced scientific instruments may not be sensitive enough to detect their influence directly. The mathematical complexity of theories involving higher dimensions also poses a significant challenge. While mathematics can describe additional dimensions, translating these abstract concepts into testable predictions or observable phenomena remains a formidable task. This gap between theoretical models and experimental evidence makes it difficult to confirm or refute the existence of higher dimensions conclusively. Furthermore, the energy scales required to potentially access or manipulate higher dimensions are far beyond our current technological capabilities. Some theories suggest that probing extra dimensions might require energies comparable to those present in the early universe, which are unattainable with our present particle accelerators and experimental setups. This technological limitation further complicates efforts to gather empirical evidence for the existence of higher dimensions. Scientists approach skepticism about higher dimensional theories with a combination of rigorous mathematical frameworks, theoretical predictions, and ongoing efforts to find observable evidence. These theories, which propose the existence of dimensions beyond the familiar 3 spatial dimensions and 1 time dimension, arise from attempts to unify fundamental forces and explain puzzling aspects of our universe. One key strategy is to develop testable predictions. For example, some higher dimensional models suggest that gravity might behave differently at very small scales, or that certain particle interactions could reveal signs of extra dimensions. Scientists design experiments to search for these effects, using particle accelerators, precision gravity measurements, and astronomical observations. Researchers also emphasize the explanatory power of higher dimensional theories. These models can potentially resolve long-standing issues in physics, such as the hierarchy problem in particle physics or the nature of dark matter and dark energy. By showing how extra dimensions could solve multiple puzzles simultaneously, scientists build a case for their plausibility. Furthermore, scientists engage in open dialogue with skeptics, addressing concerns and refining theories based on critiques. They acknowledge the speculative nature of these ideas while highlighting their mathematical consistency and connection to established physical principles. This approach of transparency and continuous refinement helps maintain scientific integrity and fosters progress in our understanding of the cosmos. Our current mathematical models for describing higher dimensions are powerful tools, but they come with significant limitations. While these models allow us to conceptualize and work with dimensions beyond the 3 spatial dimensions and 1 time dimension we experience, they struggle to fully capture the complexities of higher dimensional spaces. One major limitation is our inability to directly observe or measure higher dimensions. This means our models are largely theoretical and cannot be easily verified through experimentation. We can make predictions based on these models, but confirming their accuracy becomes increasingly challenging as we move beyond the 4th dimension. Another constraint lies in our cognitive abilities. The human brain evolved to understand and navigate a 3-dimensional world, making it difficult for us to truly comprehend the nature of higher dimensional spaces. Our mathematical models serve as abstract representations, but they cannot overcome this fundamental limitation of human perception. Furthermore, as we increase the number of dimensions in our models, the computational complexity grows exponentially. This makes it increasingly difficult to perform calculations and simulations involving many dimensions, even with the most advanced computers. As a result, our ability to explore and analyze higher dimensional systems is often limited by practical computational constraints. The quest to understand the fundamental nature of our universe often leads scientists to explore theories that extend beyond our familiar 3 spatial dimensions and 1 dimension of time. Higher dimensional theories, such as string theory, propose the existence of additional spatial dimensions to explain various phenomena in physics. However, these theories face a significant challenge due to the lack of direct observational evidence. Our inability to directly observe or measure these extra dimensions stems from their proposed extremely small size and the limitations of our current technology. These additional dimensions are theorized to be compactified or curled up at scales far smaller than what our most advanced instruments can detect. This makes it incredibly difficult to find concrete proof of their existence, leaving scientists in a predicament where elegant mathematical models suggest their presence, but empirical confirmation remains elusive. This absence of direct evidence has led to intense debates within the scientific community about the validity and usefulness of higher dimensional theories. Critics argue that without observable proof, these theories remain in the realm of speculation and cannot be considered truly scientific. Proponents, on the other hand, point to the theory's explanatory power and mathematical consistency as reasons to continue exploring them. The challenge of finding evidence for higher dimensions has pushed scientists to develop innovative, indirect methods of detection. These include searching for specific particle interactions in particle accelerators, looking for gravitational effects in precision measurements, and analyzing cosmic radiation for signs of extra-dimensional influence. Despite these efforts, conclusive evidence remains out of reach, highlighting the ongoing challenge that the lack of direct observational evidence poses to higher dimensional theories. Our exploration of higher dimensions is significantly hampered by the inherent limitations of our 3-dimensional existence. The human brain and sensory systems have evolved to perceive and interact with a world of length, width, and height, making it challenging to conceptualize or directly observe additional spatial dimensions. Current technology, while advanced, is fundamentally based on principles that operate within our observable 3-dimensional universe. Instruments and sensors are designed to detect and measure phenomena in this familiar realm, leaving us ill-equipped to directly probe or manipulate higher dimensional spaces. Mathematical models and theoretical physics provide frameworks for understanding higher dimensions, but translating these abstract concepts into practical, observable experiments remains a formidable challenge. We lack the means to generate or control the enormous energies that might be required to access or influence higher dimensional phenomena. Furthermore, our computational capabilities, while impressive, are still insufficient to fully simulate or analyze the complexities of higher dimensional systems. The exponential increase in variables and interactions in additional dimensions quickly overwhelms even our most powerful supercomputers. limiting our ability to model and predict behavior in these realms. Reconciling higher dimensional theories with established physics presents a fascinating challenge for researchers. These theories, such as string theory, propose the existence of additional spatial dimensions beyond the three we observe in our everyday lives. While this concept might seem at odds with our conventional understanding of the universe, scientists have developed ingenious ways to make these ideas compatible with known physical laws. One key approach involves the idea of compactification. This concept suggests that extra dimensions exist but are curled up or compacted to incredibly small scales, far beyond our current ability to detect them directly. These compact dimensions could be as small as the Planck length, the smallest measurable distance in physics. At larger scales, the effects of these extra dimensions become negligible, explaining why our familiar three-dimensional world appears as it does. Another method researchers use is called dimensional reduction. This mathematical technique allows scientists to describe higher dimensional theories in terms of lower dimensional models that match our observed reality. By carefully choosing how to reduce these extra dimensions, researchers can preserve the essential features of the higher dimensional theory while making predictions that align with established physical laws. Experimental physicists are also working to test the predictions of these higher dimensional theories. They search for subtle effects that might reveal the presence of extra dimensions, such as minute deviations in gravitational force at very small distances, or the creation of microscopic black holes in particle accelerators. While no conclusive evidence has been found yet, these ongoing experiments continue to refine our understanding and push the boundaries of known physics. Funding plays a crucial role in advancing research on higher dimensions, enabling scientists to push the boundaries of our understanding of the universe. Adequate financial support allows researchers to develop and use sophisticated equipment, conduct complex experiments, and collaborate on a global scale. One of the primary ways funding impacts higher dimensional research is through the construction and operation of advanced particle accelerators. These massive machines, such as the Large Hadron Collider at CERN, require billions of dollars to build and maintain. They allow physicists to recreate conditions similar to those in the early universe, potentially revealing evidence of extra dimensions. Funding also supports theoretical research, providing mathematicians and physicists with the resources to explore abstract concepts and develop new mathematical models. This theoretical work is essential for formulating testable hypotheses about higher dimensions and guiding experimental design. Moreover, financial backing enables interdisciplinary collaboration, bringing together experts from various fields to tackle the complex challenges of higher dimensional research. This collective effort, made possible by adequate funding, accelerates progress and increases the likelihood of groundbreaking discoveries that could revolutionize our understanding of the cosmos and the nature of reality itself. Researchers treading the line between theoretical physics and speculation engage in a delicate balancing act. They rely on established scientific principles and mathematical models to form hypotheses about the nature of our universe. These theories often push the boundaries of our current understanding, exploring concepts that may seem fantastical at first glance. To maintain scientific rigor, physicists subject their ideas to rigorous mathematical analysis and peer review. They seek to make predictions that can be tested through observation or experimentation, even if current technology limitations prevent immediate verification. This approach allows them to explore groundbreaking concepts while adhering to the scientific method. However, when venturing into realms beyond our observational capabilities, such as the nature of dark matter or the existence of parallel universes, researchers must clearly distinguish between well-supported theories and more speculative ideas. They often use phrases like, "according to our current understanding," or "this model suggests," to indicate the level of certainty in their statements. The scientific community plays a crucial role in this process, critically examining new theories and demanding evidence before accepting them. This collective scrutiny helps separate promising avenues of research from less substantiated speculation, guiding the field of theoretical physics toward productive and scientifically sound investigations of our universe's deepest mysteries. Understanding higher dimensions could revolutionize our technological capabilities in ways we can scarcely imagine. By grasping the nature of dimensions beyond our familiar three spatial dimensions and time, scientists and engineers might unlock new methods of energy production, transportation, and communication. In the realm of energy, higher dimensional physics could reveal untapped sources of power. Theories suggest that gravitational forces might be stronger in higher dimensions, potentially allowing us to harness gravity more effectively for energy generation. This could lead to more efficient and powerful energy systems, transforming how we power our world. Transportation could see dramatic advancements through higher dimensional understanding. If we could manipulate additional spatial dimensions, we might develop methods to create shortcuts through space-time, enabling faster-than-light travel or instantaneous transportation between distant points. This would revolutionize space exploration and global travel, shrinking vast cosmic distances to manageable scales. In the field of computing and information processing, higher dimensions could pave the way for quantum computers of unparalleled power. By utilizing the properties of particles existing in multiple dimensions, we might create computers capable of solving complex problems that are currently intractable, advancing fields like cryptography, drug discovery, and climate modeling. Higher dimensional theories open up fascinating possibilities for space exploration. These theories suggest our universe may have more dimensions than the three spatial dimensions and one time dimension we commonly experience. If true, this could revolutionize our understanding of space travel and the cosmos itself. One intriguing implication is the potential for shortcuts through space. In a higher dimensional universe, what appears to be vast distances in our observable three-dimensional space might be much shorter paths through extra dimensions. This concept, often called a wormhole, could theoretically allow rapid travel between distant points in space. Such a breakthrough would dramatically alter our approach to exploring the cosmos, potentially bringing far-flung star systems within reach. These extra dimensions might also explain phenomena we struggle to understand within our current framework. Dark matter and dark energy, which together make up most of the universe's mass energy, could be manifestations of these hidden dimensions. Unraveling this mystery could provide new insights into the structure and evolution of the universe, guiding our exploration efforts. Moreover, higher dimensional theories might lead to new propulsion technologies. If we could harness the energy or forces present in these extra dimensions, we might develop more efficient spacecraft engines. This could solve one of the biggest challenges in space exploration: the enormous energy requirements for interstellar travel. By tapping into higher dimensions, we might find ways to traverse the cosmos that are currently beyond our imagination. Higher dimensional concepts have fascinating applications in computer science and artificial intelligence. In machine learning, these ideas enable algorithms to process and analyze data with many variables or features. Neural networks, for instance, operate in high-dimensional spaces, allowing them to recognize complex patterns and relationships that would be difficult to discern in lower dimensions. Dimensionality reduction techniques like principal component analysis help manage the complexity of high-dimensional data. These methods extract the most important features from large datasets, making them more manageable for analysis and visualization. This is crucial for handling the vast amounts of information generated in fields such as genomics, climate science, and social network analysis. In quantum computing, higher dimensional concepts play a vital role. Quantum bits or qubits can exist in multiple states simultaneously, unlike classical bits. This property, known as superposition, allows quantum computers to perform certain calculations exponentially faster than traditional computers. The ability to manipulate these higher dimensional quantum states is key to developing powerful quantum algorithms. Researchers are also exploring how higher dimensional geometries might improve artificial neural networks. By incorporating concepts from topology and manifold learning, scientists aim to create more efficient and flexible AI models. These advanced architectures could potentially lead to breakthroughs in areas such as natural language processing, computer vision, and autonomous systems. Understanding higher dimensions could revolutionize medical science in ways we can scarcely imagine. One intriguing possibility is the development of advanced imaging techniques that allow doctors to see the human body from entirely new perspectives. By tapping into higher dimensional space, medical professionals might be able to observe organs and tissues from angles that are impossible in our three-dimensional world, potentially revealing hidden abnormalities or providing new insights into complex biological structures. Another fascinating application could be in the field of drug design. Scientists might use higher dimensional models to better understand the intricate folding patterns of proteins, which play crucial roles in many diseases. This enhanced comprehension could lead to the creation of more effective medications that target specific molecular structures with unprecedented precision. Surgical procedures could also be transformed by higher dimensional knowledge. Surgeons might be able to perform operations with greater accuracy by manipulating tools through additional spatial dimensions, minimizing damage to surrounding tissues and reducing recovery times. This could be particularly beneficial for delicate procedures involving the brain or nervous system. Furthermore, our understanding of genetics and DNA could be dramatically expanded. The complex coiling and uncoiling of DNA strands might be better explained and manipulated using higher dimensional models, potentially unlocking new treatments for genetic disorders or even allowing for more advanced gene editing techniques. Higher dimensional theories, such as string theory and M theory, propose that our universe may have more than the 4 dimensions we commonly experience. These additional dimensions could potentially revolutionize our approach to energy production and storage in ways that seem almost like science fiction. One intriguing possibility is the concept of extracting energy from these hidden dimensions. If we could access and harness the energy contained within these extra spatial dimensions, it could provide an almost limitless source of clean energy. This theoretical energy reservoir might dwarf our current energy sources, offering a solution to our growing global energy demands. In terms of energy storage, higher dimensional theories suggest the possibility of compact energy storage systems that utilize these extra dimensions. Imagine being able to store massive amounts of energy in devices that appear small in our three-dimensional space but extend into other dimensions. This could lead to incredibly efficient and compact batteries or energy storage units, potentially revolutionizing industries from electric vehicles to renewable energy systems. Furthermore, these theories might allow for new methods of energy transfer. If we could manipulate objects or energy through higher dimensions, we might find ways to transmit power over vast distances with minimal loss, or even instantly, overcoming many of the current limitations in energy distribution. While these ideas remain highly speculative, they illustrate how higher dimensional theories could potentially transform our understanding and utilization of energy in the future. Higher dimensional understanding could revolutionize telecommunications in ways we can scarcely imagine. Our current communication systems operate primarily in 3 spatial dimensions plus time. However, if we could harness the properties of higher dimensions, we might unlock entirely new methods of transmitting information. One potential application involves the concept of quantum entanglement. In higher dimensions, particles could be entangled across vast distances, potentially allowing for instantaneous communication regardless of physical separation. This could eliminate issues of signal delay and greatly enhance the speed and efficiency of global communications. Furthermore, higher dimensional spaces might provide novel ways to encode and compress data. Just as 3-dimensional objects can cast 2-dimensional shadows, information from higher dimensions could be projected into our familiar 3-dimensional space, potentially allowing for exponentially greater data storage and transmission capacities. Additionally, understanding higher dimensions could lead to the development of communication channels that bypass traditional obstacles. Signals might be routed through extra-dimensional pathways, avoiding interference from physical barriers or electromagnetic disturbances in our three-dimensional world. This could result in more reliable and secure communications, transforming industries from mobile networks to satellite communications and beyond. Higher dimensional concepts could fundamentally transform transportation by unlocking new pathways and methods of movement that are currently inconceivable in our three-dimensional world. Imagine vehicles that can traverse not just forward, backward, left, and right, but also through additional spatial dimensions. This could potentially allow for drastically shortened travel times by taking routes that literally cut through the fabric of space itself. One intriguing possibility is the concept of wormholes, theoretical tunnels through space-time that could connect distant points in the universe. If we could harness and stabilize these higher dimensional structures, we might be able to create shortcuts across vast cosmic distances. This could revolutionize not just Earth-bound travel, but also open up the possibility of practical interstellar exploration. On a more local scale, higher dimensional transportation could solve many of our current traffic and congestion problems. Vehicles operating in additional spatial dimensions would have more routes available, reducing bottlenecks and allowing for more efficient movement through crowded urban areas. This could lead to cities designed in entirely new ways, taking advantage of these extra-dimensional spaces for both transportation and infrastructure. However, it is important to note that these concepts remain largely theoretical. The challenges of engineering vehicles and infrastructure that can interact with higher dimensions are immense, and we are still far from understanding how to manipulate space-time in this way. Nonetheless, the potential for higher dimensional concepts to revolutionize transportation continues to inspire scientists and engineers to push the boundaries of what we consider possible. Higher dimensional theories could open up intriguing new avenues for cryptography. These advanced mathematical concepts might allow for the development of more complex and secure encryption methods. By utilizing the properties of higher dimensions, cryptographers could potentially create algorithms that are extremely difficult to crack using conventional computing methods. One possible application involves using the geometry of higher dimensional spaces to encode information. This could lead to encryption schemes that are fundamentally different from current techniques, potentially offering greater security against quantum computing attacks. The increased complexity and additional degrees of freedom provided by higher dimensions might allow for the creation of more intricate and robust cryptographic protocols. Another potential application lies in the field of quantum cryptography. Higher dimensional theories could inform the development of new quantum key distribution systems, enhancing the security of quantum communication networks. These advanced mathematical frameworks might also contribute to the design of post-quantum cryptography algorithms, which aim to remain secure even in the face of powerful quantum computers. Furthermore, higher dimensional theories could inspire novel approaches to steganography, the practice of hiding information within other data. By leveraging the properties of higher dimensional spaces, it might be possible to conceal larger amounts of data more effectively, making it even more challenging for unauthorized parties to detect the presence of hidden information. The frontier of higher dimensional physics continues to push our understanding of the universe to new limits. One of the most intriguing questions researchers are grappling with is the potential existence of extra dimensions beyond the four we experience in our everyday lives. Scientists are exploring whether these hidden dimensions could explain fundamental aspects of our universe, such as the nature of dark matter or the unification of gravity with other fundamental forces. Another pressing question revolves around the holographic principle, which suggests that our three-dimensional universe might be a projection of information stored on a two-dimensional surface. This concept challenges our perception of reality and space-time, prompting physicists to investigate how higher dimensional theories could reconcile this principle with our observed universe. Researchers are also delving into the implications of string theory, which proposes that the fundamental constituents of the universe are tiny vibrating strings existing in multiple dimensions. A key question is whether we can devise experiments or observations to detect evidence of these extra dimensions, potentially revolutionizing our understanding of the cosmos. The nature of quantum gravity remains another crucial area of inquiry. Scientists are exploring how higher dimensional models might bridge the gap between quantum mechanics and general relativity, potentially unlocking the secrets of black holes, the Big Bang, and the ultimate fate of the universe. These questions not only push the boundaries of theoretical physics, but also promise to reshape our fundamental understanding of reality itself. Quantum computing holds immense potential for revolutionizing higher dimensional research. These advanced computers harness the principles of quantum mechanics, allowing them to process information in ways that classical computers cannot. This unique capability makes quantum computers particularly well-suited for tackling complex problems in theoretical physics and cosmology. One of the most significant impacts of quantum computing on higher dimensional research is its ability to simulate and model complex systems with numerous variables. Traditional computers struggle with these tasks due to the exponential increase in computational power required as dimensions increase. Quantum computers, however, can handle these multidimensional problems more efficiently, potentially unlocking new insights into the nature of higher dimensions. Furthermore, quantum computing could aid in the exploration of string theory, which posits the existence of additional spatial dimensions beyond the three we observe. These extra dimensions are incredibly small and difficult to detect, but quantum simulations might help scientists better understand their properties and potential effects on our universe. This could lead to breakthroughs in our understanding of fundamental physics and the structure of reality itself. Advancements in quantum computing may also enable researchers to process and analyze vast amounts of data from astronomical observations and particle physics experiments more quickly and accurately. This enhanced data processing capability could reveal subtle patterns or anomalies that might indicate the presence of higher dimensions, potentially providing empirical evidence for theories that have long remained in the realm of pure mathematics and theoretical physics. Machine learning and artificial intelligence are poised to revolutionize our exploration of higher dimensions. These advanced computational tools offer unprecedented capabilities to analyze complex data sets and identify patterns that might elude human perception. In the realm of theoretical physics, AI algorithms can help scientists sift through vast amounts of data generated by particle accelerators and cosmic observations. These systems can detect subtle correlations and anomalies that could indicate the presence of extra dimensions or provide clues about the nature of dark matter and dark energy. Artificial intelligence also plays a crucial role in simulating and visualizing higher dimensional spaces. While humans struggle to conceptualize dimensions beyond the familiar three of space and one of time, AI can process and represent these abstract concepts in ways that make them more accessible to researchers. This ability could lead to breakthroughs in string theory and other models that propose the existence of additional spatial dimensions. Furthermore, machine learning algorithms can assist in developing new mathematical frameworks to describe higher dimensional phenomena. By analyzing existing theories and experimental data, AI might uncover novel approaches or suggest modifications to current models, potentially bridging the gap between quantum mechanics and general relativity in the search for a unified theory of everything. Future space missions will play a crucial role in expanding our understanding of dimensions. As we venture deeper into space, we'll gain new perspectives on the fabric of space-time and the fundamental nature of our universe. Advanced telescopes and observatories in space will allow us to detect gravitational waves with unprecedented precision. These ripples in spacetime could provide evidence for extra dimensions predicted by string theory. By studying these waves, scientists might uncover hidden dimensions that are folded into the structure of our universe. Interplanetary and interstellar missions will test our theories about the nature of space and time. As spacecraft travel at increasingly high speeds and experience extreme gravitational fields, they'll help us verify or challenge our current models of relativity. These missions could reveal how space and time behave in ways we haven't yet imagined, potentially uncovering new dimensional properties. Quantum experiments conducted in the unique environment of space could also shed light on the relationship between quantum mechanics and gravity. This could lead to breakthroughs in our understanding of how dimensions interact at the smallest scales, bringing us closer to a unified theory of physics and a deeper comprehension of the dimensional structure of our universe. Mathematicians and physicists are continually pushing the boundaries of our understanding of higher dimensions. One exciting area of development is in the field of string theory, which proposes that our universe may have up to 11 dimensions. To study these complex structures, researchers are developing new mathematical tools and frameworks. Calabi-Yau manifolds are a key concept in this field. These are six-dimensional geometric shapes that could potentially describe the extra dimensions proposed by string theory. Mathematicians are working on new ways to classify and understand these intricate structures, which could provide insights into the fundamental nature of our universe. Another promising framework is twistor theory, originally developed by Roger Penrose. This approach aims to unify quantum mechanics and general relativity by representing space-time points as geometric objects in a higher dimensional space. Recent advancements in twistor theory are offering new perspectives on particle physics and gravity. Researchers are also exploring the concept of emergent dimensions, where higher dimensional spaces arise from more fundamental lower dimensional structures. This work involves developing new mathematical models that could explain how our familiar four-dimensional spacetime might emerge from a more basic reality. Research into higher dimensions could profoundly reshape our understanding of consciousness. Scientists and philosophers have long grappled with the nature of awareness, and exploring realms beyond our familiar three spatial dimensions might offer new insights. One intriguing possibility is that consciousness itself could be a higher dimensional phenomenon. Just as a two-dimensional being would struggle to comprehend three-dimensional space, our three-dimensional minds might be limited in perceiving the true nature of consciousness. Higher dimensional models could potentially explain aspects of awareness that currently seem mysterious or inexplicable. Furthermore, some theories propose that our brains might act as receivers, tuning into consciousness that exists in higher dimensions. This concept aligns with certain interpretations of quantum mechanics, suggesting that the quantum realm, which often behaves in counterintuitive ways, might be better understood through higher dimensional frameworks. If consciousness interacts with or emerges from quantum processes, as some researchers speculate, then higher dimensional models could provide a more complete picture of how awareness arises. Exploring higher dimensions could also shed light on altered states of consciousness, near-death experiences, and other phenomena that challenge our current understanding. By expanding our conceptual toolkit, we might develop new ways to investigate and explain these experiences, potentially bridging the gap between subjective awareness and objective reality. Current research in higher dimensional theory is pushing the boundaries of our understanding of the universe. Scientists are exploring the possibility of additional spatial dimensions beyond the three we experience in our everyday lives. These extra dimensions, if they exist, could help explain some of the most perplexing questions in physics. One exciting area of study involves the search for evidence of extra dimensions in particle accelerator experiments. Researchers hope that by colliding particles at extremely high energies, they might detect signs of particles or forces leaking into or from these hidden dimensions. Such a discovery would revolutionize our understanding of the fundamental structure of reality. Another promising avenue is the development of new mathematical models that incorporate higher dimensions. These models could potentially unify different branches of physics, such as quantum mechanics and general relativity, which have long resisted integration. A successful unified theory would provide a more complete picture of how the universe operates at all scales. Advancements in gravitational wave astronomy might also offer insights into higher dimensions. As our ability to detect and analyze gravitational waves improves, scientists speculate that we might find evidence of gravitational effects from other dimensions. This could open up entirely new ways of studying the cosmos and testing theories about the nature of space and time. Higher dimensional research opens up new avenues for exploring the origin of the universe, potentially revolutionizing our understanding of cosmic beginnings. Scientists are investigating the possibility that our universe might be part of a larger, multidimensional structure, which could explain some of the mysteries surrounding its formation. One intriguing concept is the idea that our three-dimensional universe might be a membrane, or brain, floating in a higher dimensional space. This model suggests that the Big Bang, rather than being the absolute beginning of everything, could have been the result of a collision between two such brains. This perspective could help explain the rapid expansion of the early universe and provide insights into the nature of dark energy and dark matter. String theory, which proposes the existence of additional spatial dimensions beyond the three we observe, offers another framework for understanding the universe's origins. In this view, the fundamental constituents of reality are tiny, vibrating strings existing in multiple dimensions. The interactions of these strings in higher dimensions could have given rise to the universe as we know it, potentially explaining the seemingly arbitrary physical constants that govern our cosmos. Furthermore, higher dimensional models might help resolve the puzzle of quantum gravity, unifying our understanding of the very large and the very small. This unified theory could provide a more complete picture of the universe's earliest moments, shedding light on how space, time, and matter emerged from the primordial state. As researchers continue to explore these higher dimensional concepts, we may gain profound new insights into the true nature of our cosmic origins. Biologists are venturing into fascinating new territory by exploring the concept of higher dimensions in living systems. This cutting-edge research bridges the gap between biology and theoretical physics, offering fresh perspectives on how life operates at fundamental levels. One area of focus is the study of protein folding. Scientists are investigating whether the complex three-dimensional structures of proteins might be better understood by considering them in four or even higher dimensional spaces. This approach could potentially reveal hidden patterns and relationships that are not apparent when limited to our usual three-dimensional view. Another intriguing avenue of research involves the examination of neural networks in the brain. Some researchers propose that the intricate web of connections between neurons might be more accurately modeled using higher dimensional mathematics. This could provide new insights into how our brains process and store information, potentially revolutionizing our understanding of cognition and consciousness. Evolutionary biologists are also exploring how the concept of higher dimensions might apply to the development and diversification of life over time. By considering evolutionary processes in higher dimensional spaces, they hope to uncover new explanations for the patterns of biodiversity we observe in nature and gain a deeper understanding of the forces driving evolution. Higher dimensions play a crucial role in modern cosmological theories, expanding our understanding of the universe beyond the familiar three spatial dimensions and one dimension of time. String theory, a leading candidate for a unified theory of physics, proposes that our universe actually contains 10 or 11 dimensions. Most of these extra dimensions are thought to be tightly curled up and incredibly small, existing at scales far smaller than an atom. These additional dimensions could help explain some of the most perplexing questions in physics. For instance, they might account for the weakness of gravity compared to other fundamental forces, as gravity could be leaking into these extra dimensions. Higher dimensions also provide a framework for understanding parallel universes or the multiverse concept, where our observable universe might be just one of many existing in a higher dimensional space. In the context of cosmology, these extra dimensions offer potential solutions to problems like the nature of dark matter and dark energy. Some theories suggest that dark matter particles might be capable of moving through these hidden dimensions, explaining why they interact so weakly with ordinary matter. Similarly, the accelerating expansion of the universe, attributed to dark energy, could be a consequence of gravity behaving differently in higher dimensions. While these higher dimensional models remain theoretical and challenging to test experimentally, they continue to drive research and shape our understanding of the cosmos. As technology advances and new observational techniques emerge, scientists hope to find evidence that could support or refute these higher dimensional theories, potentially revolutionizing our view of the universe. Chemists are pushing the boundaries of molecular modeling by incorporating higher dimensional concepts, revolutionizing our understanding of complex chemical systems. Traditional three-dimensional models, while useful, often fall short when describing the intricate interactions and behaviors of molecules. By venturing into higher dimensions, researchers can capture a more complete picture of molecular dynamics and properties. One key application of higher dimensional concepts is in describing the potential energy surfaces of molecules. These surfaces represent all possible configurations a molecule can adopt and the energy associated with each state. While we typically visualize these in 3 dimensions, the reality is far more complex. Chemists now use mathematical frameworks that can accommodate dozens or even hundreds of dimensions to accurately represent all the degrees of freedom in a molecular system. This higher dimensional approach is particularly valuable when studying protein folding, a process crucial to understanding many biological functions and diseases. The folding landscape of a protein is incredibly complex, with countless possible conformations. By using higher dimensional models, researchers can better predict how proteins will fold and interact with other molecules, potentially leading to breakthroughs in drug design and disease treatment. Furthermore, higher dimensional concepts are proving invaluable in the field of quantum chemistry. Quantum systems inherently involve multiple interacting particles, each with their own set of variables. By employing higher dimensional mathematics, chemists can more accurately model these quantum interactions, leading to improved predictions of molecular properties and reactivity. This advanced modeling is driving progress in areas such as catalyst design, materials science, and nanotechnology. Higher dimensional theories have found intriguing applications in computer graphics and animation, pushing the boundaries of visual representation and computational techniques. These advanced mathematical concepts allow artists and programmers to create more complex and realistic simulations, enhancing the depth and richness of digital environments. One significant application is in the realm of geometric modeling. By utilizing higher dimensional spaces, designers can create more intricate and flexible models. This approach allows for smoother transitions between different shapes and forms, resulting in more fluid and natural-looking animations. It also enables the representation of complex objects that would be difficult or impossible to model in traditional 3-dimensional space. Another important use of higher dimensional theories is in the field of lighting and rendering. By considering light as a higher dimensional phenomenon, graphics engineers can develop more sophisticated algorithms for calculating how light interacts with surfaces and materials. This leads to more realistic shadows, reflections, and overall lighting effects in computer-generated scenes, greatly enhancing the visual quality of animations and virtual environments. Furthermore, higher dimensional concepts are employed in motion planning and character animation. By representing movement and poses in higher dimensional spaces, animators can create more nuanced and lifelike character motions. This approach allows for smoother blending between different animations and more precise control over complex movements, resulting in characters that move and interact with their environment in a more convincing manner. Economists are increasingly turning to higher dimensional models to unravel the intricacies of complex markets. These sophisticated tools allow researchers to analyze multiple variables simultaneously, providing a more comprehensive view of economic systems. Traditional economic models often relied on simplified assumptions and limited variables. However, modern computational power enables economists to incorporate vast amounts of data into their analyses. These higher-dimensional models can account for numerous factors such as consumer behavior, market trends, global events, and even psychological influences on decision-making. One key advantage of these advanced models is their ability to reveal hidden patterns and relationships that might be overlooked in simpler analyses. By examining interactions between multiple variables, economists can better predict market fluctuations and identify potential risks or opportunities. This approach is particularly valuable in studying interconnected global markets, where changes in one sector can have far-reaching consequences. Moreover, higher dimensional models enable economists to simulate various scenarios and test policy interventions virtually. This capability allows policymakers to assess the potential impacts of their decisions before implementation, leading to more informed and effective economic strategies. As these models continue to evolve, they promise to enhance our understanding of complex market dynamics and improve economic forecasting. Higher dimensions have become increasingly relevant in modern approaches to consciousness studies, offering intriguing possibilities for explaining the complex nature of human awareness. Researchers exploring consciousness through the lens of higher dimensions draw inspiration from theoretical physics and mathematics, particularly string theory and M-theory. These theories propose that our universe may consist of more than the 4 dimensions we typically experience: 3 spatial dimensions and 1 of time. Some models suggest the existence of 10, 11, or even more dimensions. In consciousness studies, these additional dimensions are seen as potential spaces where the phenomenon of consciousness might operate or originate. One compelling idea is that consciousness might be a higher dimensional phenomenon that projects into our 4-dimensional reality. This concept aligns with certain philosophical views, such as the notion that our conscious experiences are shadows or projections of a more fundamental reality. Proponents argue that this framework could help explain the subjective, non-physical nature of consciousness and its apparent separation from the physical brain. Critics of these approaches caution that while higher dimensional models of consciousness are fascinating, they remain highly speculative and challenging to test empirically. Nevertheless, exploring consciousness through the lens of higher dimensions continues to inspire new ways of thinking about the age-old question of how subjective experience arises from the physical world. Geologists are expanding their understanding of Earth's complex systems by applying concepts from higher dimensional mathematics. This innovative approach allows scientists to analyze and model intricate relationships between various geological processes that were previously difficult to comprehend using traditional methods. One key area where higher dimensional concepts are proving valuable is in the study of plate tectonics. By considering the Earth's crust as a multidimensional surface, geologists can better model the interactions between tectonic plates, including subduction zones, transform faults, and spreading centers. This advanced perspective enables more accurate predictions of earthquake activity and volcanic eruptions. Climate science is another field benefiting from higher dimensional analysis. Geologists are using these mathematical tools to explore the interconnections between atmospheric conditions, ocean currents, and land surface processes. By mapping these relationships in multiple dimensions, scientists can create more sophisticated climate models that account for the intricate feedback loops within Earth's climate system. Furthermore, higher dimensional concepts are enhancing our understanding of Earth's interior structure. Geologists are applying these mathematical frameworks to seismic data, allowing for more detailed mapping of the planet's core, mantle, and crust. This approach is revealing new insights into the dynamics of Earth's internal heat distribution and its effects on surface geology. Higher dimensional theories have profoundly influenced information theory, expanding our understanding of how data can be structured and transmitted. These theories suggest that information might exist in dimensions beyond the three spatial dimensions and one time dimension we commonly experience. One significant impact has been in the realm of quantum information theory. By considering higher dimensions, researchers have developed new models for quantum communication and computation. These models allow for more complex entanglement states and potentially more efficient ways of processing and transmitting quantum information. In the field of error correction, higher dimensional theories have led to the development of more robust codes. By encoding information across multiple dimensions, these codes can better protect data against noise and interference, leading to more reliable communication systems. Higher dimensional approaches have also influenced data compression techniques. By mapping data onto higher dimensional spaces, researchers have found new ways to represent and compress information, potentially leading to more efficient storage and transmission methods in our increasingly data-driven world. The concept of higher dimensional control could profoundly impact human behavior and decision-making by challenging our fundamental understanding of free will and consciousness. If our reality is indeed influenced or controlled by higher dimensions beyond our perception, it might lead to a re-evaluation of personal agency and responsibility. Individuals might experience a shift in their approach to problem-solving and long-term planning. Knowing that unseen factors could be at play, people may become more open to considering unconventional solutions or exploring seemingly unrelated avenues when faced with challenges. This expanded perspective could foster creativity and innovation across various fields. On a societal level, the idea of higher dimensional control could influence legal and ethical frameworks. Questions of accountability and intent might need to be reconsidered if actions are potentially influenced by forces beyond our three-dimensional understanding. This could lead to significant changes in how we approach justice, rehabilitation, and social norms. Moreover, this concept might impact spiritual and philosophical beliefs, potentially bridging the gap between science and mysticism. It could encourage a more holistic worldview, where individuals see themselves as part of a larger, interconnected cosmic system. This shift in perspective might foster greater empathy, environmental consciousness, and a sense of universal responsibility among humans. The concept of higher dimensional influence could have profound implications for legal systems, challenging fundamental notions of causality, free will, and responsibility. If our universe is indeed influenced by higher dimensions, it might suggest that events and decisions are predetermined or influenced by factors beyond our current understanding or control. This could potentially impact criminal law, where the concept of mens rea or guilty mind is crucial. If human actions are significantly influenced by higher dimensional forces, it might call into question the degree of individual culpability. Defense attorneys might argue that their clients' actions were inevitable due to higher dimensional influences rather than a result of conscious choice. Civil law could also be affected, particularly in areas such as contracts and torts. The idea of informed consent and voluntary agreement might need to be re-evaluated if higher dimensional influences are seen to play a role in decision-making. Similarly, the concept of negligence might need to be redefined if actions are partially determined by forces beyond our perceived reality. However, it is important to note that these potential impacts are highly speculative and would require substantial evidence and acceptance of higher dimensional influence before they could be seriously considered in legal contexts. For now, legal systems continue to operate on the assumption of individual agency and responsibility within our observable universe. The concept of higher dimensional control could significantly reshape political ideologies by introducing new perspectives on power, governance, and the nature of reality itself. This idea suggests that our perceived three-dimensional universe might be influenced or controlled by entities or forces existing in higher dimensions beyond our direct observation or comprehension. Such a paradigm shift could lead to a re-evaluation of traditional political structures and ideologies. Some might argue that current political systems are inadequate to address the complexities of a multidimensional reality, potentially giving rise to new forms of governance that attempt to account for these higher dimensional influences. This concept could also impact how we view individual and collective agency within political systems. If higher dimensional entities are seen as having significant control over our reality, it might lead to a sense of reduced human autonomy in political decision-making. Conversely, it could inspire efforts to understand and potentially harness these higher dimensional forces for the benefit of society. Furthermore, the idea of higher dimensional control might blur the lines between science, politics, and spirituality, potentially leading to new ideological frameworks that integrate these traditionally separate domains. This could result in political movements that seek to align human governance with perceived higher dimensional principles or laws. Belief in higher dimensional control could have profound psychological impacts on individuals and societies. This concept suggests that beings or forces from dimensions beyond our perceivable reality might be influencing or controlling our world. Such beliefs can lead to a sense of cosmic insignificance, as people may feel their actions and choices are predetermined or manipulated by unseen entities. For some, this belief might foster feelings of helplessness or fatalism, potentially reducing motivation to take action or make changes in their lives. They might rationalize personal setbacks or global issues as the unavoidable result of higher dimensional interference. Conversely, others might find comfort in this idea, viewing it as a form of cosmic order or purpose that gives meaning to otherwise chaotic or inexplicable events. This belief could also spark intense curiosity and a drive to understand the nature of reality. It might lead people to explore fringe sciences, metaphysics, or spiritual practices in an attempt to connect with or comprehend these higher dimensions. In extreme cases, it could result in paranoia or conspiracy thinking, as individuals attempt to discern patterns or hidden meanings in everyday occurrences. Ultimately, the psychological effects of believing in higher dimensional control would likely vary greatly depending on individual personalities, cultural contexts, and the specific nature of the belief system. It could range from existential anxiety to a sense of cosmic connectedness, profoundly shaping how people perceive themselves and their place in the universe. The concept of higher dimensions could revolutionize educational systems by expanding our understanding of reality and challenging traditional modes of thinking. As we explore the possibilities of dimensions beyond our familiar 3 spatial dimensions and 1 time dimension, we open up new avenues for learning and problem-solving. In mathematics and physics curricula, the study of higher dimensions would encourage students to think abstractly and visualize complex spatial relationships. This could lead to enhanced spatial reasoning skills and improved ability to tackle multifaceted problems. Students might develop new mathematical models and computational techniques to represent and analyze higher dimensional phenomena. The exploration of higher dimensions could also foster interdisciplinary learning. For instance, it could bridge gaps between mathematics, physics, computer science, and even philosophy. Students might engage in discussions about the nature of reality, consciousness, and the limits of human perception, integrating scientific knowledge with philosophical inquiry. Moreover, the concept of higher dimensions could inspire innovative teaching methods. Educators might use virtual reality or augmented reality technologies to help students visualize and interact with higher dimensional objects and spaces. This immersive approach could make abstract concepts more tangible and accessible to learners of all ages. The confirmation of higher dimensional control would fundamentally reshape our understanding of reality and profoundly impact society. This revelation would likely trigger a paradigm shift in scientific, philosophical, and religious thinking. Scientific institutions would undergo a radical transformation as researchers scramble to understand and potentially harness higher dimensional forces. Funding for physics and cosmology would likely skyrocket, with new fields of study emerging to explore the implications of this discovery. Religious and spiritual beliefs would face significant challenges and potential upheaval. Some faiths might interpret higher dimensional control as evidence of divine influence, while others could struggle to reconcile their doctrines with this new reality. We might see the rise of new belief systems centered around higher dimensional entities or forces. On a societal level, this revelation could lead to widespread existential questioning and potentially social unrest. People might grapple with feelings of insignificance or lack of free will if our reality is controlled by higher dimensions. Conversely, it could inspire a sense of cosmic connection and purpose, fostering greater unity among humanity as we collectively face this new understanding of our place in the universe. The concept of higher dimensional control could profoundly impact human relationships in ways we can scarcely imagine. If our reality is indeed influenced by forces beyond the three spatial dimensions and one time dimension we commonly experience, it could reshape our understanding of free will, decision-making, and interpersonal connections. Consider the possibility that our choices and interactions are shaped by influences from higher dimensions. This could mean that the chemistry between two people, the conflicts that arise in relationships, or even the serendipitous meetings that lead to lifelong bonds might be orchestrated by forces beyond our current comprehension. It raises questions about the nature of compatibility and whether what we perceive as chance encounters are actually carefully choreographed events in a higher dimensional landscape. Furthermore, if higher dimensions play a role in our relationships, it might explain phenomena that seem inexplicable within our current framework. The feeling of déjà vu in a new relationship, inexplicable instant connections, or even the sense of having known someone in a past life could potentially be explained by interactions occurring in dimensions we cannot directly perceive. This perspective could lead to a more holistic and interconnected view of human relationships, where individual connections are seen as part of a larger, multidimensional tapestry. However, it is crucial to approach this idea with scientific skepticism. While the concept of higher dimensions is rooted in theoretical physics, their direct influence on human affairs remains speculative. As we continue to explore the nature of our universe, we may uncover new insights that bridge the gap between theoretical higher dimensions and the practical realities of human relationships. The concept of higher dimensional influence could have profound economic implications, stretching our understanding of resource allocation and market dynamics. If entities or forces from higher dimensions could interact with our three-dimensional world, it might fundamentally alter our approach to scarcity and abundance. Traditional economic models based on limited resources could become obsolete if higher dimensional interactions allow access to previously unimaginable sources of energy or materials. This could lead to a paradigm shift in how we value goods and services, potentially disrupting entire industries and creating new ones. Financial markets might experience unprecedented volatility as higher dimensional influences introduce variables beyond our current predictive capabilities. The very nature of supply and demand could be transformed if higher dimensional entities can manipulate our reality in ways we cannot fully comprehend or counteract. Moreover, the potential for higher dimensional communication or travel could revolutionize trade and labor markets on a cosmic scale. Earth-based economies might need to adapt to compete or collaborate with civilizations operating under entirely different physical and economic principles, reshaping global power structures and redefining the concept of comparative advantage in an interstellar or interdimensional context. Several competing theories attempt to explain phenomena often attributed to higher dimensions. String theory proposes that our universe consists of 10 or 11 dimensions, with most of these dimensions curled up so small we cannot perceive them. This theory suggests that fundamental particles are actually tiny vibrating strings, and their different vibrations give rise to the particles and forces we observe. An alternative view comes from loop quantum gravity, which does not require extra dimensions. Instead, it describes space-time as a network of loops and lines at the quantum scale. This theory aims to reconcile general relativity with quantum mechanics without invoking additional dimensions. Holographic principle theories propose that our three-dimensional universe might be a projection of information stored on a two-dimensional surface, similar to how a hologram creates a three-dimensional image from a flat surface. This concept challenges our understanding of dimensionality and suggests that what we perceive as higher dimensions could be emergent properties of a lower dimensional system. Some researchers explore the idea of parallel universes or the multiverse, where our universe is one of many existing simultaneously. While not directly related to higher dimensions, these theories often intersect with concepts of extra dimensions and offer alternative explanations for certain cosmological observations. Holographic universe theories and higher dimensional models offer intriguing perspectives on the nature of our cosmos, each approaching the mysteries of the universe from different angles. The holographic principle suggests that all the information contained within a region of space can be described on its boundary. This concept draws parallels to how a two-dimensional hologram can represent a three-dimensional image. In the context of our universe, this theory proposes that the information about our three-dimensional reality might be encoded on a two-dimensional surface, much like data on the event horizon of a black hole. This idea challenges our conventional understanding of space, time, and the very fabric of reality. Higher dimensional models, on the other hand, posit that our universe exists within a larger framework of dimensions beyond the three spatial dimensions and one time dimension we experience. These extra dimensions could be compact and curled up, invisible to our everyday perception, or they might be vast and expansive. While these theories might seem at odds, they are not necessarily mutually exclusive. Some physicists have explored ways to reconcile holographic principles with higher dimensional models, suggesting that our perceived reality might be a holographic projection of information stored in higher dimensions. This synthesis of ideas continues to push the boundaries of theoretical physics and our understanding of the cosmos. The anthropic principle serves as a thought-provoking concept in discussions about universal control and the nature of our existence. This principle suggests that the observable universe must have properties that allow for the development of conscious life, as we can only observe a universe in which we exist. In the context of universal control, the anthropic principle raises intriguing questions about the apparent fine-tuning of cosmic constants and physical laws. Many scientists have noted that even slight alterations to fundamental forces or particle properties could render the universe inhospitable to life as we know it. This observation has led to speculation about whether our universe might be one of many in a vast multiverse, or if some form of cosmic design might be at play. Critics argue that the anthropic principle is a form of selection bias, as we can only observe a universe compatible with our existence. However, proponents contend that it provides a framework for understanding why our universe appears so precisely calibrated for life. This debate touches on deeper questions about the nature of reality, the limits of scientific inquiry, and the potential for overarching control or purpose in the cosmos. The anthropic principle thus serves as a bridge between scientific observation and philosophical contemplation, encouraging us to consider our place in the universe and the factors that have allowed for our existence. It reminds us that our very ability to ponder these questions is intimately tied to the specific conditions of the cosmos we inhabit. Simulation theories propose that our reality might be a sophisticated computer simulation created by an advanced civilization. This concept intersects with the idea of higher dimensional influence in intriguing ways. Higher dimensions, beyond the three spatial dimensions and one time dimension we experience, could potentially house the architects of such a simulation. These higher dimensional beings might have capabilities far beyond our comprehension, able to manipulate and control our simulated reality in ways that seem miraculous or impossible to us. From our perspective within the simulation, their actions could appear as inexplicable phenomena or even as the fundamental laws of physics that govern our universe. The relationship between simulation theories and higher dimensional influence also touches on the nature of consciousness and reality itself. If our universe is indeed a simulation running in a higher dimensional space, it raises questions about the true nature of our existence and the limits of our perception. What we consider to be the entirety of reality might be just a small part of a much larger, more complex system. Furthermore, this connection between simulation and higher dimensions could explain some of the puzzling aspects of quantum mechanics and other scientific mysteries. Phenomena that seem counterintuitive or impossible in our perceived reality might be the result of higher dimensional processes or interventions in the simulation, manifesting as quantum oddities or cosmic enigmas in our observable universe. The apparent fine-tuning of the universe has led scientists to explore several alternative explanations beyond the idea of a purposeful design. One prominent theory is the multiverse hypothesis, which suggests our universe is just one of countless others, each with different physical constants and laws. In this scenario, we simply happen to exist in a universe compatible with life, while countless others may be inhospitable. Another explanation is the anthropic principle, which argues that we observe a universe that appears fine-tuned because it is the only type of universe in which observers like us could exist. This principle does not explain why the universe is the way it is, but rather why we perceive it as finely tuned. Some physicists propose that the fundamental constants of our universe are not fixed, but have varied over time or space. This theory suggests that what appears to be fine-tuning might be the result of a dynamic process we do not yet fully understand. Additionally, ongoing research in areas such as string theory and quantum mechanics may eventually reveal deeper underlying principles that explain the apparent fine-tuning without requiring multiple universes or cosmic coincidences. As our understanding of physics and cosmology continues to evolve, new explanations may emerge. The quest to unravel this mystery drives much of modern cosmological research, pushing the boundaries of our knowledge about the fundamental nature of reality. Cyclic universe models present an intriguing alternative to traditional cosmological theories, challenging the idea that our universe requires higher dimensional control or external intervention. These models propose that the universe undergoes endless cycles of expansion and contraction, eliminating the need for a singular beginning or end. In cyclic scenarios, the universe experiences a series of big bangs and big crunches, each cycle resetting the cosmic clock. This repetitive process occurs within the confines of our four-dimensional space-time, potentially negating the necessity for additional dimensions to explain the universe's origin or evolution. The self-contained nature of cyclic models suggests that the fundamental laws of physics might be sufficient to govern the universe's behavior across infinite cycles. This concept reduces the reliance on external factors or higher dimensional influences to explain cosmic phenomena. However, cyclic universe theories face their own challenges, such as explaining how information and physical laws persist across cycles. Despite these hurdles, these models continue to intrigue cosmologists as they offer a compelling alternative to the need for higher dimensional control in our understanding of the universe. Quantum entanglement is a fascinating phenomenon that has captured the imagination of scientists and philosophers alike. This strange quantum effect occurs when two particles become inextricably linked, regardless of the distance between them. When we measure one particle, we instantly know the state of its entangled partner, even if it is located on the opposite side of the universe. This mind-bending concept has led some theorists to propose that quantum entanglement might play a role in the interconnectedness of the entire universe. The idea suggests that everything in the cosmos could be subtly linked through a vast network of entangled particles, creating a cosmic web of information that spans the entirety of space and time. While this notion is certainly intriguing, it is important to note that the scientific community remains divided on whether quantum entanglement can truly operate on such a grand scale. Some researchers argue that the delicate nature of quantum states makes it unlikely for entanglement to persist across cosmic distances or withstand the complex interactions of large-scale systems. Nevertheless, the concept of quantum entanglement continues to inspire new avenues of research and theoretical exploration. Scientists are actively investigating how this quantum phenomenon might influence our understanding of space, time, and the fundamental nature of reality itself. As our knowledge of quantum mechanics grows, we may uncover new insights into the intricate workings of our interconnected universe. Emergent gravity theories propose that gravity is not a fundamental force, but rather arises from the collective behavior of microscopic quantum processes. These theories suggest that space-time and gravity emerge from more basic underlying phenomena, much like how fluid dynamics emerges from the interactions of countless water molecules. When we consider higher dimensional control in relation to emergent gravity, we enter a realm of intriguing possibilities. Some theories posit that our observable four-dimensional universe might be embedded within a higher dimensional space. In this context, the emergence of gravity could be influenced or controlled by processes occurring in these extra dimensions. One way to envision this is to imagine our universe as a membrane floating in a higher dimensional bulk. The interactions and dynamics within this bulk could give rise to the gravitational effects we observe in our four-dimensional world. This concept aligns with certain string theory models, which require extra dimensions to maintain mathematical consistency. The relationship between emergent gravity and higher dimensional control highlights the potential for a deeper, more fundamental understanding of the nature of space, time, and gravity. It suggests that what we perceive as the force of gravity might be a shadow or projection of more complex processes occurring beyond our immediate perception, opening up new avenues for exploring the fundamental structure of our universe. The concept of higher dimensional control fascinates scientists and philosophers alike. One compelling argument in favor of this idea is the potential to explain puzzling aspects of our universe. Some theorists propose that forces or entities existing in higher dimensions could influence or even govern the behavior of our three-dimensional reality. This could account for unexplained phenomena in physics, such as the nature of dark matter or the inconsistencies between quantum mechanics and general relativity. Another argument supporting higher dimensional control is the mathematical elegance of theories that incorporate extra dimensions. String theory, for instance, requires multiple dimensions to reconcile various fundamental forces. If these extra dimensions exist, it is conceivable that they could exert some form of control or influence over our observable universe. However, there are strong arguments against the notion of higher dimensional control. The primary challenge is the lack of empirical evidence. Despite extensive searches and experiments, scientists have yet to find concrete proof of extra dimensions or their effects on our world. Critics argue that if higher dimensions were truly controlling our reality, we should be able to detect their influence more readily. Furthermore, the principle of Occam's razor suggests that simpler explanations should be preferred over more complex ones. Many scientists contend that invoking higher dimensional control unnecessarily complicates our understanding of the universe when more straightforward explanations might suffice. The debate continues, driving further research and exploration into the nature of our reality and the potential existence of higher dimensions. Our understanding of higher dimensions is poised for significant advancements in the coming decade. Theoretical physicists and mathematicians are continuously refining their models of multidimensional spaces, pushing the boundaries of our comprehension beyond the familiar three spatial dimensions and one dimension of time. String theory, a prominent framework in theoretical physics, posits the existence of 10 or 11 dimensions. As computational power increases and new mathematical tools are developed, scientists may be able to test some predictions of string theory, potentially providing empirical evidence for these extra dimensions. This could revolutionize our understanding of the fundamental nature of reality. Quantum computing is another field that could dramatically impact our grasp of higher dimensions. These advanced computers operate on principles that seem to defy our everyday experience of space and time. As quantum computers become more powerful, they may allow us to simulate and explore higher dimensional systems in ways that are currently impossible. Advances in cosmology and astrophysics might also contribute to our understanding of higher dimensions. Some theories suggest that evidence of extra dimensions could be found in the cosmic microwave background or in the behavior of gravity at very large scales. New telescopes and observatories coming online in the next decade might capture data that supports or challenges these ideas, reshaping our cosmic perspective. Higher dimensional research could lead to groundbreaking paradigm shifts in physics, fundamentally altering our understanding of the universe. One potential shift involves the unification of fundamental forces. By exploring higher dimensions, scientists might discover a framework that seamlessly combines gravity with the other known forces, resolving long-standing conflicts between quantum mechanics and general relativity. Another significant change could come from our understanding of dark matter and dark energy. Higher dimensional models might reveal that these mysterious components of the universe are actually manifestations of extra spatial dimensions, invisible to our current methods of observation, but crucial to the fabric of reality. The nature of time itself could be revolutionized through higher dimensional research. We might discover that time is not a singular dimension, but a complex, multifaceted aspect of reality with multiple branches or layers. This could lead to new theories about the origin and evolution of the universe, challenging our current concepts of the Big Bang and cosmic inflation. Lastly, higher dimensional studies could transform our view of parallel universes and the multiverse. Instead of separate, disconnected realities, we might find that other universes exist in higher dimensions, potentially accessible through specific physical processes. This could open up entirely new fields of study and technological possibilities, reshaping our place in the cosmos. The concept of higher dimensional control has profound implications for our understanding of reality. If proven, it would radically alter our perception of the universe and our place within it. This idea suggests that our three-dimensional world might be influenced or even controlled by entities or forces existing in higher dimensions beyond our direct perception. Proving the existence of higher dimensional control would force us to reevaluate fundamental aspects of physics, philosophy, and even spirituality. It could potentially explain phenomena that currently defy our scientific models, such as quantum entanglement or the nature of consciousness. Such a discovery might reveal that what we consider free will is actually influenced by higher dimensional factors, challenging our notions of autonomy and decision-making. On the other hand, if higher dimensional control were definitively disproven, it would reinforce our current understanding of the universe as a self-contained system governed by the laws of physics as we know them. This outcome would lead us to seek alternative explanations for unexplained phenomena and potentially drive us to explore new avenues of scientific inquiry within the framework of our observable dimensions. Regardless of the outcome, the very process of investigating higher dimensional control pushes the boundaries of our scientific and philosophical thinking. It encourages us to question our assumptions about reality and drives us to develop new tools and methodologies for exploring the nature of existence. This pursuit of knowledge, whether it ultimately proves or disproves the concept, expands our worldview and deepens our understanding of the cosmos. As scientists delve deeper into the mysteries of higher dimensions, we must carefully consider the ethical implications of this research. One key concern is the potential impact on our understanding of reality itself. If we discover that our universe is just one of many in a vast multiverse, how might this affect our sense of purpose and place in existence? We need to ensure that our pursuit of knowledge does not lead to existential crises or widespread philosophical upheaval. Another important consideration is the responsible use of any technologies that may arise from higher dimensional research. If we develop methods to manipulate or access these dimensions, we must establish strict protocols to prevent misuse. The power to potentially alter the fabric of space-time or interact with parallel universes could have far-reaching consequences that we cannot fully predict. We must also consider the allocation of resources for this type of research. While exploring higher dimensions is undoubtedly fascinating, we need to balance it against other pressing scientific needs and societal challenges. Ethical guidelines should ensure that funding and effort are distributed in a way that maximizes benefits for humanity as a whole. Lastly, we need to address the potential for unintended consequences. As we push the boundaries of our understanding, we may inadvertently disrupt natural processes or unleash forces beyond our control. Establishing safeguards and conducting thorough risk assessments will be crucial in navigating the uncharted territory of higher dimensional research. Balancing speculation and scientific rigor in exploring cosmic concepts is a delicate yet crucial task. Scientists and researchers must constantly navigate the line between pushing the boundaries of our understanding and adhering to established scientific principles. This balance is achieved through a combination of rigorous methodology, peer review, and open-minded exploration. The scientific method serves as the foundation for maintaining rigor. Researchers formulate hypotheses based on existing knowledge and observations, then design experiments or make predictions that can be tested and potentially falsified. This approach ensures that even speculative ideas are grounded in a framework that can be scrutinized and verified. However, the nature of cosmic exploration often requires us to venture beyond what we can directly observe or test. In these cases, scientists use mathematical models, computer simulations, and extrapolations from known physics to make educated guesses about the nature of the universe. These speculative ideas are valuable as they can guide future research and inspire new ways of thinking about cosmic phenomena. The key to maintaining balance lies in clearly distinguishing between well-established facts, current theories, and more speculative concepts. By being transparent about the level of certainty in different ideas, scientists can push the boundaries of knowledge while maintaining the integrity of the scientific process. This approach allows for exciting exploration of new concepts while ensuring that our understanding of the universe remains rooted in verifiable evidence and sound reasoning. Public engagement is crucial in discussions about higher dimensions, as these complex concepts have far-reaching implications for our understanding of the universe. Scientists and educators should strive to make these ideas accessible to a wider audience, fostering curiosity and critical thinking about the nature of reality. By involving the public in discussions about higher dimensions, we can bridge the gap between cutting-edge theoretical physics and everyday understanding. This engagement helps demystify abstract concepts and allows people to grasp the potential impact of these ideas on our view of the cosmos. Moreover, public engagement can inspire the next generation of scientists and thinkers. When people from diverse backgrounds are exposed to these mind-expanding concepts, it can spark new perspectives and innovative approaches to problem-solving. This collaborative exchange of ideas between experts and the general public can lead to fresh insights and drive scientific progress. Ultimately, public engagement in discussions about higher dimensions promotes scientific literacy and critical thinking skills. It empowers individuals to question, explore, and appreciate the complexity of our universe, fostering a more informed and scientifically curious society. The exploration of higher dimensions is propelling science into uncharted territories, promising to revolutionize our understanding of the universe. This quest is not merely an abstract mathematical exercise, but a fundamental pursuit that could unlock the deepest secrets of reality. Theoretical physicists are at the forefront of this endeavor, using advanced mathematics to model universes with dimensions beyond the familiar 3 spatial dimensions and 1 of time. String theory, for instance, proposes that our universe might contain as many as 10 or 11 dimensions, most of which are imperceptible to us. Understanding higher dimensions could provide solutions to long-standing scientific puzzles. It might explain the weakness of gravity compared to other fundamental forces, reconcile quantum mechanics with general relativity, and even account for dark matter and dark energy. These insights could lead to breakthroughs in particle physics, cosmology, and our understanding of the universe's origin. Moreover, the study of higher dimensions is inspiring new technologies. Quantum computing, which harnesses the principles of quantum mechanics, can be seen as a way of exploiting higher dimensional spaces for information processing. As this field advances, it could revolutionize cryptography, drug discovery, and complex system modeling, reshaping industries and scientific research methods alike.